हाँ मैं बात करता हूँ. Good morning, Anshu sir. Am I audible, sir?
Yeah, very good morning, sir. You're audible.
How are you, sir?
I'm good. I hope you're good as well.
Yeah, sir, I'm good as well. So my request is, as we are doing the live streaming of this webinar on YouTube, so what we usually do, we will take up the questions from YouTube and post on your chat window, sir.
Sure.
So it's my humble request during the session, if possible, kindly consider those questions as well from the other participants that are on live on YouTube, sir.
Definitely, sure.
Okay, thank you, sir. Thank you. Sir, we will go start within the next 10 minutes, sir, by 11.
Sure. All right.
Okay, thank you, sir.
Thank you.
Good morning, Hina ma'am. मैम आपका माइक म्यूट है.
हाँ जी सर.
Okay, I am audible, ma'am. Hello.
Hello.
Hina ma'am, am I audible? हिना मैम, मेरा आवाज आ रहा है आपको?
हाँ सर.
ओके मैम. Hina ma'am? Hina ma'am?
Hello.
Ma'am, please start.
Okay, sir. Welcome everyone to the second day of the FDP. The topic for the day is convolutional neural network and programming CNN with Python. I would take the opportunity of introducing our today's speaker, Mr. Anshu Pandey. Mr. Anshu Pandey is a data scientist, AI consultant, and a technical trainer having an experience of working with more than 30 MNCs from IT services, banking, finance, manufacturing, aeronautics, and telecom. He has trained and built data science teams for enterprises like Ericsson, JP Morgan, Chase and Company, etc. Consulted on projects to McKinsey, BNP Paribas, TechTrunk. He successfully delivered projects on recommendation of pricing of taxi services, employee attrition, resource management, IT project budget, and timeline prediction. So, without further delay, I would like to invite Mr. Anshu Pandey to begin with today's session.
Thank you, ma'am. And so let me go ahead and share my screen. Hello, everyone, and very good morning. Very good morning, and welcome you all to this webinar. My name is Anshu Pandey, and as I'm already introduced to the audience, I'll give a short introduction again. So yeah, I work as a program director for San Francisco-based company, Pura Ventures, and I lead the technical part of the business, which is sister concern company for Pura Academy. By qualifications, I'm masters in automatic control and robotics, and I'm Microsoft certified trainer. I am a Wiley certified trainer. Work as a data scientist, and so far I have worked with multiple organizations to help them build their data science teams and also plan out their AI and data science transformation journey. I'm currently mentoring and monitoring a few of the projects for a few of our clients across Southeast Asia, in Middle East, and also in North America. That's about me, and let's get started with the topic. So the topic today is convolution neural networks and programming of CNNs with Python. So in this case, CNNs are mostly used for tasks related to computer vision. So we're going to be looking at more in detail in this talk about what exactly neural networks are, and specifically how CNNs work, and how the process of convolution work actually, and how do we program them in general, and how do we build standard CNNs with Python using TensorFlow autoencoders. So yeah, that's going to be the idea. That's going to be the objective of this particular session today. So let's get started. So initial few hours will be, I will say around 1 hour will be spending on understanding neural networks. So it is a little expected that you have fair idea of machine learning, you have fair idea of possibly Python programming, and you have fair understanding of introduction or basics of neural networks. But yeah, that I'm going to take in detail as well. So in case you do not have idea, or maybe you have any question, please feel free with that. Okay, so let me minimize the screens and camera so that you can see more part of the screen. Okay, and at any point, feel free to ask questions, put your questions in the chat or in the comment section. And yeah, so stay active in questions. Let's get started. So basically, first, we're going to be talking about the idea of what exactly are neural networks. So neural networks are one of the many machine learning algorithms, but they are one of the very powerful machine learning algorithms. They are inspired from a biological network of artificial neuron in human brain. And these are, you can say, sample ML algorithms. This is a typical representation of neural network, actually. Other than that, neural networks are nonlinear models, nonlinear algorithms. That means they can learn complex nonlinear relationship between the features and the target for any data set whether you talk about the use case of data science or NLP or computer vision, for any such scenario, if there's a complex nonlinear relationship between the features and the target, neural networks can learn that quite effectively. They are black box model. That means they are not explainable to business. So you cannot explain with a business objective how exactly neural network is taking decisions, and neural networks are taking decisions or making predictions. So for that reason, we do not prefer using neural networks in data science. So neural networks are very less used, right? So I would say very less used in data science, right? Reason being, neural networks are black box model, and we cannot understand, we cannot explain it to business team on what account the predictions are done. So most of the applications of neural networks you'll find are there in the field of computer vision and natural language processing, where you get to deal with unstructured data, that is images, videos, and text and audio, right? Well, the examples that we're going to be looking at today are part of images. And again, the same thing works on videos as well, right? So, well, that's one nutshell idea. All right, let's go forward and talk from a very basic standpoint. What exactly are neural networks? So here we go. This is a very fundamental structure of a neuron, the way it looks like in human brain. Well, don't worry about it. You don't need to have biological knowledge of neurons and human brain works, right? This is just for a referential point of view, where to start from and where exactly you can say these concepts originated. So this just to give you a contextual understanding to bring in, way that to understand why do we call it neural network, right? So essentially, it's more of a mathematical algorithm, right? A set of mathematical equations combined together. But then, how does it, match it, or how do we map it to human brain? Let's understand that. So this is a typical neuron in a human brain, right? And this part of the neuron is nucleus. These are dendrites via which the human brain accepts different input, right? If somebody is calling me, hey, Anshu, so our ears are going to be simply listening to that audio and taking the neurons connected to our ears are going to take that audio as input via dendrites to human brain, and then the brain is going to process that. So dendrites do the job of taking input, right? So dendrites simply take input. The nucleus does some processing on the input and generates some output via axon, right? That's how standard neuron works in a human brain. Dendrites take input, nucleus does some kind of computation on that, and axon generates the output. Well, it is not known what exact computation it does in natural neuron in human brain, but yes, there is a standard structure that is followed in an artificial neuron. This is an example, a typical example of how does it works, right? So this video shows a little typical example of how the neurons sort of generate input and send it to another neuron. This was just a typical mapping of it, right? Not more of this is just a typical mapping of it, not a real human brain mapping. So this is how, in human brain, neurons propagate and send signals from one neuron to another, and that's how the information goes in. So you can say the axon of one neuron sends the input, sends the output as an input to the dendrite of another neuron. And that's how multiple neurons communicate in a human brain. A human brain is a structure, or you can say a chain of neurons, millions of neurons. Each neuron acts as a computational unit, and the job of, or you can say the process of, multi-layer and multi-level computation makes the neural network a very powerful makes the human brain a very powerful computational unit, you can say, or a very powerful computational segment, I would say. Let's talk about the idea of how do we map a natural neuron to an artificial neuron. Well, So in human brain, as we know that there are lots of neurons. Some neurons take input, some neurons send those input to the neurons inside the brain, and some neurons at the end connect those new outputs to our output organs, from which we reflex, which could be our tongue, which could be our muscles. So there are lots of neurons connected to our input organs like eyes, ears, nose. A lot of neurons connected to our output organs like tongue, possibly, which with we speak up, or muscles, how do we react. Then there are millions of neurons in between these neurons. The presence of millions of neurons actually help in doing multi-level and multi-layer computation. For example, let's say that if some data is actually being captured via ear, there is an audio signal. The neuron connected to ear is going to take it to brain. This is one neuron, you can say, connected to ear, take it to brain. And then in brain, you have multiple layers of neurons, you can say. Each circle can be thought of as neuron. So this input is mapped out to each of these. Each neuron does some kind of computation. For example, let's say one neuron might identify that whether this is a, let's say, male or female, right? Or maybe these neurons might say that, let's say, male voice or female voice. Another neuron might say that either it is old age or young age. Another neuron might identify that it is my friend or family. And that's how millions of neurons compute, do very quick classification and result into identification of who is calling that, right? So our human brain quickly recognizes the voice and understands that, okay, it's my friend X or my friend Y or my brother X or my sister C, like that, or D, like that, or my father or my mother who is calling. Our brain quickly recognizes that because there's a multi-level classification that's happening in a human brain. Multiple neurons act as individual classifiers. Consequently, that generates the whole output. And that's how we get the output, and we more of take a turn. Okay, yes, who is that, right? So human brain is a multi-level computational and multi-layer computational unit, and that's what makes it powerful. So when it comes to artificial neural network, what is copied is not the way how neuron works. In artificial neural network, which is the most powerful set of algorithms today in the world of AI, what is copied, or what is, you can say, inferred, is the architecture, the multi-level and multi-layer computational unit, right? The thing which makes a human brain a very powerful computational unit is the multiple levels of computation, right? First level, male, female. Second level, young age, old age. Third level, family or outside or friend, possibly. Fourth level, maybe possibly, let's say, known friend, or maybe long known friend, something like that. So that's how multi-level computation helps in doing solving a more complex nonlinear problem. This is what the architecture is, what we copy in artificial neural network. Let's understand that even more in detail. So this is an example of a natural neuron, right? This one. How do we take input, do some computation, generate some output? Quite similar to that, there is an artificial neuron in which we also take some input, do some mathematics, we'll talk about this, and generate some output, right? So we take some input, do some mathematics, generate some output. An example of a neuron could be a sample linear regression equation. For example, let's say if your inputs are x1, x2, x3, x4, and the coefficients are m1, m2, m3, m4, and output is y hat. So this can be represented as y hat equals m1x1 plus m2x2 plus m3x3, maybe plus a constant c. So each neuron is nothing but a simple linear equation. Each neuron does nothing but a simple linear computation. On a whole neural network is a nonlinear model, but one neuron individually only performs a very simple linear computation on data. And yeah, that's nutshell idea about it, right? So this is the idea of one neuron. The way in a human brain, multiple neurons connect to each other. So you can say one neuron is going to take some input, do some computation, generate the output, which will be taken as input by another neuron, which will do some computation, generate the output. So that, like that, there's a chain of neurons, and that's how we get the network. Similarly, in human brain, in artificial neural network as well, we take one neuron, take some input, generate some output, and that output we feed it to another neuron, and which takes some input, does some computation, generates some output. Like that, we build the whole neural network. This is an example of a typical neural network. Right? So here you have a typical neural network where we have multiple neurons. Every circle points to a neuron, right? So this is a neuron, you can see. This is a neuron. In an artificial neural network, we have neurons arranged in layers. So you can see that these are different layers. Maybe layer L1, layer L2, layer L3, layer L4. Like that, we have layers of neurons. Neurons are generally in a standard neural network not connected to each other within the layer, but each layer of one neuron is connected to each layer of another neuron in a standard neural network. We call it fully connected network. Essentially, there are three types of layers: input layer, hidden layer, and the output layer. A neural network will usually have only one input layer, which is always the leftmost layer, only one output layer, which is always the rightmost layer. And all the layers between input and output are called as hidden layers. So we have one input layer here, one output layer here, and two hidden layers, right? So you can see that, you can say that in a neural network, you will have definitely at least one input and one output. The choice of hidden layer is up to us. Whether we want to have it or how many layers we want to have it is an hyperparameter. We have to decide that as a programmer or as a developer. Now, how about number of neurons? Well, the number of neurons in the input layer depend on number of features. So if I have 20 features, I will have 20 neurons in input layer. If I have 100 features, 100 neurons in input layer. Input neurons simply represent actually the features itself, whereas the number of output neurons represent number of labels. Let's say if I'm doing 5-class classification problem, I will have 5 neurons in output layer. If I'm doing 10-class classification problem, 10 neurons in output layer. If you're developing a face recognition model for 5 employees of a company, 5 neurons in output layer. For regression problems, usually we keep only one neuron if it is one label to be predicted, right? So one neuron in output layer. For 2-class classification, you have both the options of considering that as a one unit classifier, that means one neuron in output layer, or also you can take 2 neurons in output layer with a different specification of activation function. Well, so this is a typical standard architecture of one generic neural network. It could be a lot different than this as well. So I'll repeat again, the idea is that in a neural network, you have neurons arranged in layers, right? So you have multiple layers of neurons, and there are 3 types of layers. Input layer, the leftmost layer is always the input layer. The number of neurons in input layer are equal to number of features. Output layer, the rightmost layer is always the output layer. The number of neurons in output layer are equal to number of labels. Hidden layers are always the layers between input and output layers, and the number of neurons is up to us. The number of layers also is up to us. We have to decide that. So there's a question, what is the role of hidden layer? Well, we're going to talk about that. So in next 10 minutes, you will get very much clarity about what's the role of hidden layer. Why do we need that? Okay, so we have to wait for next around 10 minutes for more discussion, and we'll get the idea on that. I believe you may have more questions, but definitely in next 15 to 20 minutes of discussion will give you a lot of clarity. There's a question, how can we calculate total number of hidden layers in an ANN model? Well, it cannot be calculated. In any machine learning algorithms, there are 2 types of parameters. One is like generic parameters, the other is hyperparameters. The values of hyperparameters cannot be calculated. It has to be hit and tried. You have to hit and try that, or you have to estimate it. So it is, we never calculate the number of hidden layers in a neural network. It has to be optimized for every problem, right? For every problem, it depends on the complexity of problem, and based on that, you have to tune that. So it is a tuning parameter. That's the reason we call it hyperparameter. There's a question: did RL will be used in neural network like deep learning? Yes, I mean neural networks are used in reinforcement learning, right? So we also do reinforcement. They are very simple models of reinforcement learning, approach for reinforcement learning, and then there is something called deep reinforcement learning, which is where we use neural network as to create agents for reinforcement learning. Okay. So yep, maybe many of the answers to the questions we'll be getting in the next few minutes, right? Which is like the role of hidden layer and all, even more about it, right? And also a lot clarity on the calculation of the hidden layers in a neural network. So let's go ahead about that, and here we go. So mostly you would want to understand what happens inside a neuron, right? What exactly a neuron does. We have discussed about neural network. We talked about that, okay, they are input layer neurons, in output layer neurons, and hidden layer neurons. But one of the interesting things to know is that what exactly a neuron does, right? And how does a neural network works. So let's talk about that as well. Here we go. So I'm going to actually shift to the idea of one notebook, which is where I'm going to share the other screen. In fact, I'm going to share my main screen here. So we can talk about the idea of what exactly a neuron does in a neural network, right? So here we go. Let's talk about a sample neural network, a typical, very simple, straightforward neural network, which is, let's say this. We have 1, 2, 3 input neurons, right? So we have 1, 2, and 3 input neurons. And let's say we have 1 output neuron, right? So like that, we have total 4 neurons. So you can say that, this is possibly input layer. This is output layer. And there's no hidden layer at the moment, right? So there's no hidden layer, and that's where we'll be discussing about with hidden layer and without hidden layer, what's the difference. Okay, so now one of the rule of neural network is that all the neurons of one layer will be connected to all the neurons of next layer. So considering that, I need to make these connections, right? So let's say this is the neuron N1, N2, and possibly got switched off. This is the neuron N1, N2, N3, and this is, let's say, N4. Generally, all the neurons in input layer represent the features, right? So you can say that possibly these neurons represent the features X1, X2, and X3. Whenever a neuron is connected to any other neuron, they are connected by mathematical weightage. We call them weights, W1. So you can say W1 represents how important N1 is for N4, how much importance it should give to N1 for calculation at N4. Similarly, W2 represents the importance of N2 for N4, and W3 represents the importance of N3 for N4. And finally, as N4 is output neuron, you can say that from N4 we'll get the output, which could be, let's say, represented as Y hat. Okay. Now, in order to understand what happens, excuse me. In order to understand what happens exactly at a neural network or in a neuron, so let's understand, a few important rules of neural networks. So there are two essential important rules, which is something that we need to remember to understand neural networks. So I can say that two rules of a neural network, and that is, the first rule is the the first one is that no computation occurs at input layers of neurons. Excuse me. I just need to get some water. I'm sorry. Okay, so the first rule of neural network is that no computation occurs on the input layer of the neurons. That means input layers of neurons do not perform any mathematics, any computation on data. They are just used to represent input data to the neural network, and they do not perform any mathematics on data. Right? So that's one important rule of neural network. That means in this network, we have total 4 neurons, which is like N1, N2, N3, N4. But there's only one computational neuron, which is N4, as N1, N2, N3 are 3 part of the input layers, and they do not perform any mathematics, any computation on data. The second important rule is every computational neuron, which is in our case only one, that is N4. So every computational neuron performs 2-step mathematics, which is first weighted sum with bias, and the second one is activation function. So every computational neuron in general performs 2-step mathematics on the data. The first one is weighted sum with bias. That means it is going to simply add a bias, add a bias B with a weighted sum. So you can say that they're going to be 2-step. The first is weighted sum, and the second is activation function. The output of first, let's say, is Z equals weighted sum is simply multiplication of input with the weight, right? So you can say X1 into W1 plus multiplication of X2 into weight. So that's what you call a sum, X2, W2 plus the next one, which is X3, W3. Plus it adds a constant, which is bias, right? And yeah, that's the idea. So that's how we get weighted sum. The next step is on the output of weighted sum, just apply any activation function, right? Which could be any generic function, fx equals to x squared, fx equals to, let's say 1 by x, any generic function you can apply, but there are some standard functions that we use in general. So you apply some activation function f on the output here, and we call it fz, and that's how we get the output of N4, which is also equivalent to y hat, as N4 is our output neuron, right? So the second step is y hat equals like fz. These are the 2 simple steps that occur at every computational neuron, whether it is hidden layer or it is output layer neuron, because input layer neurons are not computational at all. So all the hidden layer or output layer neurons will perform this mathematics, 2-step mathematics, weighted sum and activation function. There's a question, is there any relationship between the number of input and output layer? There's always be one input layer, and there'll always be only one output layer. The number of neurons of input and output layers are not at all related. It is always independent of each other, right? Input layer neurons depend on how many features I have. Output layer neuron depends on how many classification or maybe regression problem do you want to solve. What is the task of that you want to achieve, or maybe what is the number of labels that you want to predict. So input and output layers are only one, but number of neurons in input layer has no relation with the count of neurons that you would want to have possibly in output layer. Right, so that's one important thing. Now these are the 2 steps that occur at every computational neuron. If I try to combine them up, we can say that it may look like y hat equals activation function f applied on x1 w1 plus x2 w2 plus x3 w3 plus, or maybe I should say w1 x1 w2 x2 w3 x3 plus b bias b, right? So this is a typical representation of a standard this current neural network, right? Combination of 2 steps, right? So this is a representation of this particular neural network, which is like combination of the 2 steps. Right. So this is a standard mathematics that occurs on every computational neuron. All right. Yeah. So that's one nutshell idea. And now this mathematics might look a little similar to this mathematics might look, quite similar to, possibly you can say, any standard regression model, which is like, in general, you can think of this as a linear regression model. So this mathematics look quite similar to linear regression model. And you might say that, this looks quite similar to the linear regression algorithm, which we have studied earlier. And that could be possibly y hat equals m1x1 plus m2x2 plus m3x3 plus c, which is mx plus c slope and intercept. Looks quite similar to that, which is correct. Let's talk about the situation in which it might look similar to that, actually. So this is actually equation of something called linear regression, which is used to solve regression problem, and it's a linear model. So if you talk about a situation, if consider the activation function, if fx, the activation function, is, let's say if I take identity function as an activation function, which is fx equals x. If identity function is activation function, this will look like very simple linear regression equation, m1 x1 m2 x2 m3 x3 plus c. That means it will do the job of linear regression. Whereas if I take activation function as sigmoid function, which is, let's say, fx equals 1 by 1 plus e power minus x, then this will do the job of logistic regression. This will do the job of logistic regression, which is actually used for classification. So this is used for regression problems, and this is used for two-class classification problem. Now, this is a very interesting point, everyone. That means, you see, the moment I change the activation function to identity, it does the job of linear regression, which is used to solve regression problems. And the moment we change the activation function to logistic, it does the job of classification problem. I mean, it does the job of logistic regression. That means classification problem when we change activation to sigmoid. That means one of the essential rule that the job of activation function on the output layer is to decide whether the neural network is going to be used for regression problem or it is going to do the job of classification problem. So by choosing different activation functions on the output layer, you can design or you can customize that what kind of problem the current neural network is going to solve. Is it going to solve a regression problem or a classification problem? For example, in this case, you see, if I take identity function as an activation function, it does the job of linear regression, solves a regression problem. And when I use sigmoid function as an activation function, it is doing the job of logistic regression and solving a classification problem. This is the essential idea of why do you need activation function on the output layer of neuron, right? We're not talking about hidden layer, but yes, why do you need activation function on the output layer of neuron? So in any neural network, how do you decide which activation function to use? Well, you can take that decision on the output layer. The activation function should be decided based on what is the type of problem are you solving. For regression, identity. For two-class classification, sigmoid. Similarly, for multi-class, we have softmax. These are different activation functions. Well, there are a few questions that I would want to answer at the moment, which is what is bias and what will be the value of bias in ANN? Well, bias is nothing but a parameter here. First, what it does, what is the job of bias? Well, the job of bias to attain the extra weighted value, which is not contributed by any of the features, right? So bias is an extra addition, and the value of weights and bias both will be attained by the neural network once the neural network is being trained. So when we train the neural network, the values of weights and bias update, and using gradient descent algorithm. The gradient descent algorithm works in the background, and it makes the neural network learn from data. And that's how neural network learn and update the values of weights and bias. So bias is a similar parameter, which is like a weight, and the optimizer, which could be gradient descent or any other optimizer, will update the values of weights and bias, both. The role of bias is to just attain extra add-on addition, which is not contributed by in the task, which is not contributed by any of the feature. An example to understand that could be, let's say if I want to, if I'm solving a problem of buying a house, Now, I might be having a housing prices prediction problem. In that case, you may have multiple features, number of bedrooms, area of the house possibly, or let's say, you might have the distance from the house to the city center, metro station, airport, railway station. A lot of these might be features. Now, what bias will do here? Well, there must be a minimum, price of the house which is not contributed by any of these features. Let's say that the price of the house might be, the price of all the houses starts from 20 lakhs. Let's say 20 lakhs in Indian currency, right? So 20 lakhs in Indian currency, which is like, let's say 200,000, right? So 200,000 rupees is the sorry to I think there's been some challenges with this. I'm sorry for the apologies for the little delay. Yeah, so back we are. I hope we're good to resume. So, well, we have been discussing around the idea of, and I missed a few questions actually. So I would request the moderator to please put those questions here. Right, I think I missed a few questions. Okay, so yeah, the recent questions, I think I missed it. All right, so yeah, the idea is about, I was answering the question regarding bias, right? So the idea of bias is to attain the extra add-on value, right? For example, in case of housing prices prediction, let's say you may have the minimum price of house as 20 lakh, which is like, let's say 2 million in currency, and that could be the minimum price of house, which is possibly not affected by any of the factors. right? So that value will be attained by bias, because that value should not get contributed by the impact of features, right? If you do not put bias, the weightage of, or you can say the calculation of that 2 million value will be actually contributed to features, and that's where the weights will get higher value and the model will become more sensitive, right? Bias can be negative and positive, both the values, and bias impacts the performance of model, as in it can make the model more sensitive. If there is no bias, the model can become more sensitive. Let me give an example to understand that. The effect of bias. Let's say that we have trained a neural network, right? So we developed a neural network in general, and this is a standard neural network with 3 input neurons, 1 output neurons, and you have x1, x2, x3, like this, right? So you have that connected, and you got a y output here, y hat. Let's say activation function is simply fx equals to x. That means there is no impact of activation function. It's an identity function. We have w1, w2, and w3. This will also answer the question, what is weighted sum, if you have the question weighted sum. And let's say that our inputs are simply x1 is maybe, we have two situations. One situation where x1 is maybe 2, x2 is 1, x3 is 1. Another situation, x1 is 4, x2 is 3, x3 is 3. And the values of weights after training the model, we got the values of weights as maybe 1000, 2000, maybe 4000. And there's no bias, right? Or let's say we have bias which is having value as 50, just a very low, or maybe it's not present as well. That can be considered. Okay, now in this situation, if I go for weighted sum in case 1, what will happen? My weighted sum will be 2 into x1 w1 plus x2 w2 plus x3 w3 plus b, which is going to be 2 into 1000, 2000 plus 1 into 2000, which is 4000 plus 1 into 4000, 8000. Right, this is my weighted sum plus bias. Okay, which is, you can say y hat as well, because the activation function is fx equals to x. In case 2, x1 w1 plus x2 w2 plus x3 w3. You see, there's a small change in values of x1, x2, x3. There's a small change in values of x1, x2, and x3, right? Now, what will happen here is 4 into w1, which is 4000, 3 into w2, which is 6000, and 3 into w3, sorry, x3 into w3, which is 4 into 3, 12,000. So it's going to be total 22,000. So now one of the thing is, with a small change in x, you see x1, x2, x3 were 2 and 1, and now it changed to 4, 3, 3. A small change in the values of feature, there is a huge change in the output. A small change in the values of feature brings a huge change in output. This is where you can see when the weights are very high or there's no bias, this is what happens. You can say that the neural network is very much sensitive to the values of input feature. A small change in values of input feature, a small deviation in values of input features will bring a very large change in the output computation. So if there is no bias, this sensitivity will be even much, much higher, right? If you look at a real-time example of this, if let's say housing prices prediction, right? So generally in housing prices prediction, the minimum price of the house could be 20 lakhs, right? 2 million Indian currencies. If you put bias, generally bias is expected to attain that calculation, or you can say addition of 20 lakhs. If you don't put bias, that 20 lakhs then will be forwarded to all other features. So you can say that maybe 5 lakhs getting added because of number of bedrooms, 4 lakhs getting added because of amount of area in the house. So these features will become very sensitive. Slight change in these values of these features, number of bedrooms, will bring huge change in the output computation, which is the price of house. But generally those 20 lakhs are not contribution to the features. Rather, it is an extra addition which is going to happen, which is going to be there for any house, for any specification. So when you don't put bias, the extra add-on, which is not actually the contribution of features, will get calculated as contribution of features, and that would make model become more sensitive, and that way model will become heavily overfitting. So bias actually stops your model or becomes a little hurdle to overfitting or becoming more sensitive to the model. That's a nutshell idea of why do you need bias in general. I hope that answers the question. So yes, it affects the presence of bias. Presence of bias will affect. The value of bias doesn't affect. It's like value of bias is just impacting the calculation, and the prediction will affect the accuracy. There's a question, you said that bias can be negative also. Yes, there can be real-time example where bias is negative. Yes, they can be. That could be, let's say, possibly, more of a data science example. I mean, in a nutshell, you see, wherever the calculations are high. Okay, let me give an example of where the bias can be negative, right? So yes, let's say I have features which are representing, let's say we have features which are representing the balance in bank account of customer. The other feature is representing the salary of customer. And the third feature is representing possibly age of customer. And the neural network is trying to predict based on these three features whether the customer will or how much amount of money the customer will spend in mall, possibly the amount of money the customer will spend in mall. Now in this case, whatever is the salary balance in the bank account, right, or possibly salary of customer, any customer is not going to sell they spend the whole salary on the in the mall, right? So these features will be taken as calculation. There'll be weighted sum happening. Maybe weights can also be negative, right? So maybe this weight is, let's say, 0.8, this weight is 0.9, and maybe this weight comes up as 0.4. Possibly this can be negative if the age has a reverse impact. Old age people spend less and young age people spend more. Weight can be negative as well. Now here it might happen that the weighted sum may become very higher, but possibly that people are not going to spend that much of money. If that's the situation or the pattern present in the data, the value of bias might become minus 1000, because whatever salary the customer gets, the same salary they are not going to spend out on the in the mall. They'll be definitely spending lower value. So the bias will be negative just to decrease amount which they usually spend lesser. So let's say that every customer spends around only 60% of their salary when they go to the mall on the shopping, right? So that 40% of reduction will be contributed by bias. Right, I hope this makes sense about where the bias can be negative. Yes, bias does not reflect on, it has no effect on the correlation of dependent and independent variable, right? It has no effect on that because it is an extra addition. It is not contributed by any feature. The way it can affect the accuracy of model is that if you do not put bias, the effect of bias, the extra addition or reduction which the bias is supposed to make will be contributed then by the features. The features, the model will learn that the features are impacting this, because that 20,000, let's say here, the reduction of 10,000 has to be done from somewhere. So it will be then happening, by the weights will change. If you don't put bias, the weights will even attain a lower or higher value. And that would make the model become a very good fit on the training data, but will become a very much sensitive model for the test data or new data. Right, so that's the nutshell idea about it. I hope it makes sense. Well, come back to this neural network discussion, everyone. So here we're going to go ahead and discuss more about this, right? Okay, so here we discussed about that the job of activation function, right? If I use activation as identity, it is doing the job of linear regression, solving a regression problem. Sigmoid, solving a logistic, and doing the job of classification. But in both the cases, it is actually a linear model. That means this neural network cannot solve complex nonlinear problems. It can only solve simple linear problems, right? So this, in both the cases, this neural network is essentially a linear model, right? That's important. Now, that means if I have two situations, let's say, if I have two situations, which could be if you have two situations, which could be, let's say, In first situation, the data distribution is like this. In second situation, the data distribution is like this. So in out of these two situations, you can say in this first situation, when x increases, y also increases, right? So when x is increasing, y is increasing. So you can say x and y have linear relationship. A straight line can represent the relationship between x and y. In the second case, for x and y, till here, when x is increasing, y is increasing. But after that, when x is increasing, y is decreasing. So a straight line like this cannot represent the overall relationship between x and y, or possibly a straight line like this cannot also represent the overall relationship between x and y. Maybe a curve like this can represent the relationship in x and y. So this is called as linear pattern, and this is called as non-linear pattern. So the current neural network, as it is resembling to linear regression or logistic regression, this neural network can only solve linear pattern, can only learn linear relationship between the features and the target, cannot learn non-linear relationship between the features and the target. This neural network is a simple linear model. So at the moment, it can solve this problem, right, which is the problem on the left, let's say case A properly, but it cannot solve case B properly. It cannot solve. The current neural network cannot solve that, right? Now, one of the reason being because it doesn't have hidden layer. Now, let's say to the same neural network, let's add a hidden layer, right? So let's talk about other formulation of the neural network where we have a hidden layer. So let's have a hidden layer. So we say we have again 3 neurons, 1, 2, and 3, 1 output neuron, but this time we have 2 hidden neurons as well, right? This time, let's say we have 2 hidden neurons as well. And so as you know, the rule that every neuron of layer 1 is going to be connected to every neuron of next layer. So this is how the neurons are going to be connected, you can say. All right. And yeah, so you can say that here we have neuron N1, N2, N3, which are representing inputs X1, X2, X3. These are N4, N5, and N6. Finally, we're getting output Y hat from here. As we know that, they are going to be weights. So let's say that this is W11, W12, W21, W22, W31, W32, the bias B1 here, the bias B2 here, W41, W42, the bias B3 here. Now, this is a sample neural network. And so in this neural network, we have total 6 neurons. If we follow the first rule of neural network, that the input layer neurons do not perform any computation on data. So you can say that N1, N2, N3 are not computational neurons. Rest N4, N5, and N6 are computational neurons. So we have total 6 neurons and 3 computational neurons here. Let's talk about the computation at N4. So at N4, you can say that the computation would be X1 into W11 plus X2 into W21, right? Plus X3 into W31. These are 3 things, which are coming to N4. Plus the bias B1. So you can say activation function F applied on X1 W11 plus X2 W21 plus X3 W31 plus bias B1. Similarly, N5 can be formulated as X1 W12 here, X2 W22 here, X3 W32 here, X1 W21, 12 plus X2 W22 plus X3 W32 plus bias B2. Now that's what we got at N4 and N5. Now output of N4 and N5 are going to be input to N6, right? So you can say N6 can be formulated as F of N4 into W41, F into W, let's say 42, or maybe we can also call it W 4-2 or maybe 5-1 as well, right? So as per the convenience. Now this is where this neural network can be represented by these three equations. So a neural network is nothing but a collection of linear equations. Every computational neuron represents one linear equation, and such collection of linear equations is what we call as a standard neural network, right? So you can think of this as three lines or maybe three equations. But when you try to play, let's say if you try to draw this on a Cartesian plane, right? So of two features possibly, right? So you can say that N4 might a straight line, N5 might be a straight line, N6 might be a straight line like this possibly. Now these three are individually are linear models, but a combination of, you can see that the three linear models altogether is actually a non-linear model, right? I mean, the combination of three linear models is actually learning a non-linear pattern. That means now this neural network is going to be able to learn a non-linear pattern like this one. Right. So now this neural network has become a non-linear model. Without hidden layer, it was a linear model. So with hidden layer, it is a non-linear model like this, and without hidden layer, it was a linear model. So neural network with hidden layer becomes a non-linear model, and without hidden layer, it's a simple linear model, cannot learn non-linear relationship between the features in the target. As many as hidden layer neurons that we increase here, that much more non-linear and complex it will become, and that much more complex patterns it will be able to learn between the features and the target. So the capability of neural network to be able to solve complex problems retains in the number of hidden layer neurons that we keep into that. The more we increase the number of hidden layer neurons, the more powerful the neural network becomes and the more complex problems it can solve, right? And so that's nutshell idea. A neural network without hidden layer is a linear model, and with hidden layer is a non-linear model. So there was a question, what is the job of a hidden layer in the neural network? The answer is that hidden layer neurons or hidden layers in general provide the capability to a neural network to be able to solve non-linear complex problems, right? So that's a nutshell idea about it. Okay, I hope that answers the question. And yeah, now I'm going to take a few more questions here. So when a neuron is linear, why collection of neurons non-linear? Yes, because one neuron is linear and collection of neurons, that means a collection of linear models. As you can see that, you know, one linear model, another linear model, and three linear models altogether, they are a non-linear. They are learning non-linear patterns. Every non-linear pattern is nothing but collection of multiple linear patterns. You can also think of this as collection of two linear models together. If I combine just two linear models, it can learn these non-linear patterns. So every nonlinear model is nothing but collection of multiple linear models, right? So when one neuron is linear, collection of neurons are nonlinear. So there's a question, kindly explain bias use and how it will affect a network. Well, the use of bias, as I said, nutshell, the use of bias simply makes the neural network learn whatever amount of prediction is not being contributed by the existing features. Is it contributed from external sources or is contributed, you can say, standalone added one? That addition is what bias learns, right? Or maybe that extra add-on is what bias learns. In a context of linear regression model, you can think of bias as y hat equals mx plus c. Y hat equals mx plus c. So this c is nothing but the bias. This is an equation of a straight line. And what is the role of straight line? What is the role of C? We call it intercept in a straight line. So in a neural network, the way an intercept represents extra addition in a straight line equation, similar way bias represents the extra addition, right? In a straight line, if you say that this is a straight line, so intercept represents this addition. In the calculation of y, whatever is extra added, which is y at x equal to 0. The value of y at x equal to 0 is what intercept is, or C is, right? And that's what bias represents. Whatever is extra added without presence of any feature, what will be the output? That's what the value bias attains, right? At value of each feature equal to 0, what will be the prediction, right? Let's say if you talk about predicting temperature. Now, if you're predicting the temperature of Mumbai, with multiple factors, what is the season, what is the month? Now, without presence of any feature, can we say that minimum temperature of Mumbai will be at least 15 degrees Celsius? That 15 degree is a minimum value, which is not contributed by the month or the week or maybe rainy season or not, maybe XYZ, which is the minimum value that will be always there in Mumbai. That value of y at all independent features equal to 0 is the extra bias or addition that is happening to the prediction. And that value is what learned by the bias, attained by the bias. Bias learns that extra addition. The value of prediction at all x equals 0. On the top of 15, then the features will help in contributing. Well, it will go 16 or 18 or 21 or 25 or 31 or 35 based on the season, based on the month. These could be different features that might contribute to the extra calculation of the outcome. I hope that gives you a little idea about bias. Then there's a question how we add hidden layers. It depends on some situation or how many neurons in hidden layer. Well, yeah, it depends on the how complex your problem is, right? Now, there's no way to calculate complexity of problem. You can assess that based on the performance analysis. So you have to start with a standard structure of neural network, check the performance of model. Are you in the zone of overfitting or underfitting? Based on that, you have to customize or tune the neural network architecture. Right. So that's the answer to the question, everyone. I hope this gives you a nutshell idea about how neural networks actually work and how do they function in general, right? Any questions, feel free with that. Put that in the chat box or the comment. All right, here we go. So these are the two important rules that we have talked about the idea of neural network. First is no computation on input layer neurons. Second is two process occur at every computational neuron, which is weighted sum and activation function. There's a question, can we apply the same weight to the hidden layers? Well, we do not put the values of weights. The values of weights always, whenever you build the neural network, are randomly initialized. Throughout the learning process, we update the values of weights using some optimizer or some algorithm. Let me give you a quick idea to that, right? So this might complete the logical understanding of how does it functions in general. My bad, just a second. Just a second. Yeah. All right. So let's say that this is a nutshell idea of the structure of how this nutshell idea structure of how the linear regression model learns. So in case of linear regression, the way it works is that we take label data, we do the cleaning of label data, right? Which is like, you can say here, we handle missing values, duplicate entries. This is the data science context, more of it. And unwanted features, encoding, scaling. We do feature engineering by doing statistical analysis, data visualization, domain understanding, and all. Once we get the best set of features, we feed it to the equation y hat equal mx plus c. From that prediction, we calculate the cost function, which could be j, which is the cost function or error function between y and y hat. In order to minimize this cost or error, we use an optimizer like gradient descent, which gives us the value of new value of m and new value of c based on the given value of m minus lr, which is learning rate into del j by del m, or learning rate into del j by del c, right? And this new value of m and c, we feed it back to the equation, and that's how our one iteration of learning completes. The same process works in case of neural network. It just here, we replace the standard linear equation by a neural network. We calculate the cost function, use gradient descent to update the values of weights and bias, and send the new values of weights and bias to the neural network again. We keep on repeating this process until the cost function stops changing less than a threshold, you can say, right? And the equation of updation is the way it was new value of m equals old value of m minus lr into del j by del m. Here it's going to be new value of weight equal to old value of weight minus lr into del j by del w. New value of bias equals old value of bias into minus lr into del j by del b. So this is how we calculate the values of weights and bias. In the very first iteration, we initialize the values of weights and bias with random values, random numbers. When we train the model with a huge amount of data, the neural network learns from that, and using gradient descent, it updates the values of weights and bias in every iteration to attain the best value. At the end of the training process, you will have best values of weights and bias. So the neural network attains or identifies the best value of bias from the data itself. Right. So technically, all the neurons should be initialized randomly, and you should not technically start with the same value. Even if you start with, if you're using backpropagation, it shouldn't be a challenge. Right. So we don't decide the values of weights. The answer is that there is a question: can we apply same weights to the bias hidden layers? First is we don't decide the values of weights. We initialize the values of weights and bias in the very first iteration, which keeps on changing in every iteration of training process, and which is updated by the gradient descent, right? So at the end of the day, when you get the neural network, your all values of weights and bias might have different values. That's not shell idea about it. There's a question: when we increase the high number of neural networks, then complexity is very high. The capability of neural network becomes higher to be able to solve more complex problems, but also that may lead to overfitting as well, which we'll discuss in a moment. We'll go to that situation, talk about it. So the idea is, yes, when you increase the number of hidden layer neurons in a neural network, that increases the capability of the neural network to be able to solve more complex problem. That increases the complexity of the model as well, and the neural network learns more deeper patterns and complex patterns, relationship between the features and the target attribute, right? So yeah, that's the nutshell idea of it. There's a question: how to work neural network in hidden layers to outcome over. I didn't get your question. Please rephrase that. There's a question: does this concept implemented in Python using some predefined functions or manually? Well, we have very powerful packages in Python which can do the whole process for us, and we don't have to write the backend mathematics. So we don't have to implement manually. That's a nutshell idea. And they are not only one, but there are multiple libraries which can help us to achieve this. All right. So yep, that's nutshell idea about it, everyone. But this is just generic understanding that we still need to have in order to be able to decide the values of hyperparameters. Well, so going further, let's go and talk more about this, right? So please ask questions, put as many as you have, right? And here we go. So we discuss about the idea of neural network, that in a neural network, no computation on input layer neurons, and every computational neurons does two-step mathematics, which is weighted sum and activation function. There's a question: how the weights are initialized and adjusted. First, the initialization is randomly done. So you can use any function to randomly start the values of weights, or maybe you can also manually put 0.5, 0.6, 1, 10, 20, 30 like that. So initialization is randomly. Adjustment is done based on the optimization algorithm that we use. A very popular and simpler optimization algorithm is gradient descent optimizer. So that can help us to adjust the values of weights and bias throughout the training process. So gradient descent does the job of adjusting, that means updating the values of weights and bias the moment you train the neural network. Right. So that's nutshell idea. I hope that answers the question. All right, so let's go further about this. There's a question: how to make a model of training and testing the model using parallel processing algorithms to reduce the time complexity. Well, with Python, you have powerful packages available which can do the job of parallel processing and parallel computation without making any specific difference. But then there are ways to achieve this in more effective way without more time complexity with the packages like PyTorch and TensorFlow. If you use the core API instead of the eager execution API like Keras. So Keras still has that option, but the core APIs gives us options of customizing even more to attain more parallel computing. So if you use, let's say in Google Colab, you can just configure the GPU computing, which will speed up the process of training of the model, right? And yeah, that's the idea, right? There's a question: what about the data types of input layer, same types or mixed? Well, when it comes to data types, input layer, originally when you take the data set, it might have mixed, but a neural network or any machine learning algorithms always accept only numbers. They don't accept anything else. If we have images, we load them and load them as pixel values and pass the pixel values, which are numbers. If we have text, we transform the text, vectorize that by using methods like text or vectorization, count vectorization, TF-IDF vectorization, or word-to-vec vectorization, and convert them into numbers, right? If we have numbers, we keep them as it is. If we have videos, we convert them into chunks of images and then load the pixel values corresponding to that. So every neural network only learns from, not only neural network, every machine learning algorithm only learns from numbers, right? No other format. And those numbers might represent category, might represent a number as well. For example, they may represent a Boolean value like 0, 1, yes, no, or they may represent a numeric attribute, which could be, let's say 20, 30, or 40, or maybe any number in a continuous range. How many hidden layers should we have when there are 3 output layers? It doesn't depend on the number of hidden layers does not depend on the number of output neurons and on input neurons as well. There's no fixed mathematical rule to decide that. It is more of intuition, and less than that, more than that, it is more of you have to say tuning. You have to tune the number of hidden layers. You have to start with, let's say, 1 hidden layer, check whether you are underfitting or overfitting, and then go ahead with more hidden layers accordingly, or less hidden layers accordingly. How to decide which activation function should be used? Yes, we're going to have that in next few slides. We're going to answer that question. All right, here we go. But with gradient descent, don't we face vanishing and exploding problem? Yes, we do definitely face that in different situations. We face this challenges in the situation of recurrent neural network, vanishing or exploding gradient, and that's where we have another solution of Lstm. So there are definitely some challenges with the optimizers that we use, and there are some solutions to that. Right, so Lstm answers or solves the problem of vanishing gradient and exploding gradient. Right, and in case, so mostly you will face the problem of vanishing or exploding gradient in case of sequential problems like time series or NLP problems. All right, so that's the idea. Let's move forward. So talking about the architecture of neural network, there are a few basic architectures, right? So there's another question. As the weights of inner layer get changed automatically, so is it true with bias, or we have to decide it? No, the same thing happens with bias also. The way weights change internally throughout the gradient descent process, the bias also change. The way we initialize the random values of weight, we initialize random values of bias. As gradient descent changes the weights, gradient descent also changes the values of bias as well. Right, so it's just bias are also similar to weights. Only difference is weights can contribute to the weighted sum function with impact of features, and bias are not impacted by features. Right, so that's an initial idea. Right, so let's say if all the features are 0, there's no value of weight, but there's still value of bias. Right, so we start values of bias as well, initialize it randomly, and then it keeps on changing internally according to the use of gradient descent for every iteration. So let's go ahead, everyone, and talk about the idea of architecture of a neural network. There are multiple architectures of neural network, but essentially 3 very simple architectures, which are single layer feed-forward neural networks, multi-layer feed-forward neural networks, and recurrent neural networks. Right, so let's talk about these. Let's talk about the idea of single layer feed forward, multi-layer feed forward, and a recurrent neural network. Single layer feed forward is a neural network which has no hidden layer. So neural network, when it has no hidden layer, we call it single layer feed forward neural network. And so we also call these neural networks as perceptron models as well, or we call them single layer perceptrons. Right, so we also call them single layer perceptrons or single layer feed forward neural network. So as these neural networks do not have hidden layer, they are simply linear in nature, and they are simply used to solve very simpler problems. Generally, like most of the cases, we don't use them, but yeah, for complex problems, for simple problems, you may want to use them. Right, so we call them perceptron models as well, and yeah, these are the single layer neural networks. The neural network with at least presence of 1 hidden layer, right? So when you have at least 1 hidden layer, we call it multi-layer feed-forward neural network, right? So when you have at least 1 hidden layer, more than 1 hidden layer is fine. More than 2 hidden layers, we call it deep neural network, right? So at least 1 input layer and at least 1 hidden and at least 1 output layer. 342 is representing the number of neurons into that. Now these are 2 examples of single layer and multi-layer. The other architecture is also maybe you might get to have a talk about this going further, as a recurrent neural network, wherein you have the output of one neuron is fed as input to another neuron in a sequential way. That's what you call as the recurrent neuron. So an example of recurrent neuron network could be, you have multiple input neurons, which could be, let's say, x1, x2, x3. So you have multiple input neurons. You may have input neurons higher than the number of features. And then we may have output neurons here, right, which are connected by all of this, right? And it generates some sort of output here, which could be y hat at time t. Now what we also do is we also feed output of y hat at time t after a certain delay as input, which is, you can say, y hat at time t minus 1. That means in a recurrent neural network, we have more input layers compared to the number of features. And we also feed the output of the previous instance of the output of neural network as an input itself, right? So you can say that, this is what we call as a recurrent neuron. So the current neuron, which is, you can say this one, is called as recurrent neuron because it is taking its own output also as input. It's just its own previous time instance output, right? So these neurons are called as recurrent neurons. This neuron is recurrent neuron. And the neural network with recurrent neurons is called as recurrent network, right? These networks are used whenever you want to solve a sequential problem. The example sequence problems could be time series problems and could also be NLP problems as well, in which you have to deal with text data or audio data. These are all part of recurrent networks, right? An example could be, let's say if I have to do stock prices prediction. So to predict stock price at 11 a.m. in the morning, I'll take all the features at 11 a.m., right? Which could be XT, X1T, X2T, X3T. But I might also want to take the price of stock predicted at 10 a.m. in the morning, right? So that is YT minus 1. That means the prediction at 10 a.m. in the morning, I may also want to take as input as well, right? And yeah, that's one important idea, right? So this is what we call as recurrent network. They are also widely used for NLP tasks like the language translation, text classification, intent recognition, and chatbots. Many of these tasks they are used for. A modification to RNN is what we widely used in NLP. We call it Lstm. So chatbots up to a large extent are backed by Lstms. They can be hidden layers as well. In a recurrent neural network, you can have hidden layer. So if you look at this network, we have 3 input neurons, 1 input neuron, 2 input neuron, and 3 input neuron. But these 3 are and 4 input neurons, in fact. So only 1 is the real input, and these 3 are you can say delayed outputs. So the neural network is taking 3 delayed outputs and 1 real input, and that's how it is doing prediction. All right. So in a recurrent neural network, you have a neuron which takes its delayed output again as input, right? So that's a nutshell idea of how an RNN looks like and it works. So yeah, let me know if you're good with this. So yes, there would be hidden layers. There can be hidden layers in the recurrent neural network as well. And in fact, you can have recurrent neurons as hidden layers as well. This question, is there only linear sigmoid softmax activation function or more? There are more, we'll talk about that. Minimize weights and bias both during the backpropagation and during the training. What is the need of dropout? We'll talk about that as well, right? So dropout is just to reset the values of weights in between the training process. Okay, so yeah, that's what the idea is, right? Have we good with this? Okay, so yeah, I hope we're good. Any question? Why vanishing gradient occurs more in RNN compared to CNN? Because RNN, you have to remember the sequence. In CNN, you don't have to remember the sequence. Vanishing gradient is an example, which works. I mean, is a logic which actually works more only in sequence-based problem, right? So the idea of vanishing gradient is what? Because it's like let's say you're reading a book called Harry Potter, which is of 500 pages. Right, 500 pages book. Now, when you start from page 1, you might like it a lot. When you are reaching to page number 200, right, that's where you might forget the concepts or maybe possibly the names which mentioned at page 1 or page 2. You might remember very well page 199 or page 198. So you are only remembering the recent input or recent patterns. You are not remembering the long-term patterns. This is what happens with RNN. So RNN, whenever any neural network learns from sequential model, it remembers the recent behavior or recent patterns, but it doesn't remember the long-term behavior, which is what leads to vanishing gradient, right? That's where the model is not able to learn the long-term impact or long-term seasonality. It is only able to learn short-term trend and short-term seasonality. And trend and seasonality are two kind of aspects of any sequence-based problem, which is what RNN solves. CNN is not used to solve sequential problem. It's used to solve causal problem. That's the reason you don't have issue of vanishing gradient in CNN. Well, what is CNN? We can talk about that. It is convolutional neural networks, right? How do we decide the initial value of delayed input? That's 0. We always start with initial value of delayed input as 0. Okay, so that's the nutshell idea, right? So the meaning of vanishing gradient is what? Let's say, if they look at the new values of weights, gradient descent formulation, new value of weight equal to old value of weight minus LR into del J by del W. Now LR is usually a value between 0 to 1. Let's say LR is 0.001. If the value of del J by del W becomes 0.04, you can say multiplication of this will become 0.00004. Now, if you subtract this much from the weight, you can say the weights are almost not changing. This is what we call as vanishing gradient, right? When the value of gradient del J by del W becomes less than 1, the multiplication of that with LR becomes almost negligible value, and the weights stop changing. This is what we call as wide series, vanishing gradient issue. But this happens mostly in sequential based problem, I would say. Example of time series data could be stock forecasting data, sales forecasting, demand forecasting are different examples of time series data. How we use RNN means application. RNNs are very sensitive actually when it comes to building applications. So we don't use RNN directly. Rather, we mostly use the modification to RNN, which is LSTM, long short-term memory. Those are widely used in application development. I believe there are more talks coming up tomorrow or day after tomorrow to talk more about LSTM. So I want to at the moment focus more on CNN. So you want to go ahead about that, everyone. And I believe there will be more speakers to whom you can ask questions about LSTM and RNN, because we have to cover the topic that we have in this given timeline today, right? So I would apologize that I may not be able to take more questions on LSTM at the moment. I would love to answer them at the end of the session today. Right. So yeah, all the RNN and LSTM related questions will be only able to take at the end of the session, everyone. But if you have any other question related topic, we'll be able to take at the moment, right? Because we have to complete the topics first, right? So here we go. All right. So yes, now there was a question about activation function. So let's talk about activation function. So in general, there are two types of activation function, linear and nonlinear. Right. So let's talk about nonlinear activation functions first. An example of linear could be identity function. The formula for that is fx equals to x. Right. So here we can talk about first nonlinear function, which is sigmoid. So sigmoid is definitely a nonlinear function, but it is the presence of sigmoid doesn't make an algorithm nonlinear, because sigmoid is not doing the contributing to the learning process. Rather, it is just doing the transformation of weighted sum. Right. So even if you have sigmoid activation function neural network, that doesn't make the neural network a nonlinear model. Only the presence of hidden layer makes the neural network a nonlinear model, not the presence of sigmoid activation functions. Right. But activation functions are generally, or any activation functions are generally used for, simply you can say transforming the output so that it can meet the required demand, you can say, right? So transforming the output so that it can meet the required demand. So sigmoid activation functions simply do the switching of value. So if I have any value which is like, let's say 500 or maybe 5,000 or maybe minus 10,000, it will always output all the values for any value of x, right? So sigmoid will for any value of x, the output of fx will always be between 0 to 1. And this is how the shape of sigmoid goes in. So for any value of x, it always transforms that to a probability between 0 to 1. We consider that probability of observation being in class 1, and we do thresholding with 0.5. So more than 0.5 we say class 1, and less than 0.5 we say class 0. Right, so that's how the sigmoid actually works. So sigmoid is the main use of sigmoid on output layer whenever you're dealing with two-class classification problem. So whenever you're dealing with two-class classification problem, we use sigmoid activation function on the output layer of the neural network. A modification to sigmoid is softmax activation function. So whenever you're dealing with multi-class classification problem, on output layer of the neural network, you will use softmax activation function. Right. So when you are dealing with two-class classification on output layer, you'll use sigmoid activation function. When you are dealing with multi-class on output layer of neural network, you will use softmax activation function. Right. These are both for output layer. Both functions are differentiable, and that's nutshell idea. Now, one of the issue with sigmoid is sometimes it may make the neural network get stuck at the training time. Right. Reason being, sigmoid always projects the value between 0 to 1. Right, it always maps out the values, the outputs, the values between 0 to 1. That means if I take average of this, the average might come to 0.5. It might happen at point that the gradient descent is trying to decrease the error less than 0.5, but the sigmoid is again in next iteration bringing it again to 0.5. Right. So this way it might create, in some cases, it does creates, it creates a hurdle in the training process, in the optimization process of the error, and it makes the neural network get stuck during the training, as sigmoid does the opposition to the training process, where the gradient descent is trying to reduce the error towards 0. In next iteration, sigmoid is again bringing it back to on an average of 0.5. That's the difficult situation. In such situation, when you're not able to optimize further and you want to improve further the performance of model, instead of sigmoid, you may want to use tanh activation function. Right. Instead of sigmoid, you may want to use tanh activation function. Tanh also has the same shape. So the way you use sigmoid for 2-class, tanh is also for 2-class. The only difference is tanh ranges between -1 to +1. So the average of this will tend to become closer to 0. And that's how it doesn't act as a hurdle, or it doesn't get the training process stuck in between. And that's where it is more preferred over sigmoid activation function. The only thing is tanh becomes computationally more expensive compared to sigmoid, as there's only one logarithmic term in sigmoid. There are two logarithmic term, exponential terms in tanh. So computational cost is higher with tanh a little, but at the same time, it is more profitable. So most of the cases we start with sigmoid, and if we are not able to optimize the performance, we kind of shift to tanh as well. So yeah, the drawback of tanh is computationally more expensive, but the benefit is it doesn't make the neural network stuck during the training process. The third and a very popular activation function is ReLU, or rectified linear units. The simple formula of ReLU is fx equals x for x greater than or equal for x greater than 0, I would say, and 0 for x less than or equal to 0. Yeah, 2-class classification is like when I want to classify cat or dog, yes or no, happy or sad, right? So emotion, happy or sad, 2-class. When you want to classify happy, surprised, and sad, multi-class. So whenever you want to do classification in yes, no, true, false, that's 2-class classification. For more than 2 categories, multi-class classification. Right. So that's the nutshell idea. Okay. So this is the idea of ReLU activation function. The benefit of ReLU is that if the weighted sum is negative, ReLU outputs the value as 0. That means if the weighted sum is negative, ReLU is going to make the output of the whole neuron become 0. That means it is going to kind of switch off the neuron and switch on the neuron based on the value of weighted sum. So ReLU does more computationally effective switching compared to sigmoid. Sigmoid also does switching, but ReLU can be also used for switching more effectively. If the switching is done more effectively, ReLU makes the neurons get activated and deactivated within the neural network, which leads the neural network to learn more complex patterns compared to without using ReLU. So what Relu does is, you can see if you use Relu on the hidden layer, at a moment it can make only certain neurons active. So this neuron is active and contributing to prediction. This neuron is inactive, not contributing to prediction. This neuron is inactive. These neurons are inactive and not contributing to prediction. So the use of Relu on hidden layer makes the neurons active or deactivated, and that's how the neural network learns more complex behaviors and more complex patterns with the help of Relu. So one of the best choice to make on the hidden layers of neural network is to use Relu activation function. So in almost every neural network, whenever it comes to choosing a activation function on hidden layer of neural networks, which is computationally more effective, at the same time it is powerful to make the neural network learn complex patterns, is Relu. Right? So that's the idea. That's a nutshell idea about it, right? And so these are different activation functions. In some cases, Relu might lead to dead neurons. In those situations, we have a leaky Relu function, which is like fx equals to x if x is greater than 0. And instead of 0 for negative, it makes it 0.001. So we call it leaky Relu. This is used whenever Relu leads to dead neurons. That means some of the features are not at all contributing to prediction. Irrespective of changing the values of those features, you find that there is no change in output. That means they are neurons which are dead neurons. And in that situation, you don't want to change the activation function to leaky Relu. That's a nutshell idea, but this is mainly for optimization. You would not want to start with leaky Relu. You would always want to start with Relu. And in case you are finding out some dead neurons, you can check it, change it to leaky Relu as well. That's a nutshell idea. There's a question why we use softmax for multi-class classification, because for multi-class classification, you want multiple probabilities, and then you would want to pick the probability which is the highest one. And that's where you would want to go for softmax, because Sigmoid gives you only one probability, and you have to do thresholding of that probability with 0.5, less than 0.5, greater than 0.5. So you can do one time thresholding, but you cannot do multiple time thresholding. And that's where softmax does the job. It gives you the weighted sum of probability. That means if I'm using 10 neurons on output layer, each of them I'm using softmax activation function. So output I'll get is 10 probabilities. The sum of 10 probabilities will be 1, and the highest probability is my class. So softmax makes the neural network learn that this observation is belonging to which out of multiple classes, right? And it gives always a higher probability for that class and lesser probability for all other classes, right? So always to make one selection out of many, softmax does the job. Okay, so that's nutshell idea about this, right? So this is nutshell idea about the activation functions in general. Now that's about the basics of neural networks we have discussed, and now we want to shift to the idea of convolutional neural network, and that's where we want to shift to the idea of the concept of deep learning. Right, so now we can talk about the concept of deep learning and in general convolutional neural network. Right, so well, in general, deep learning is nothing but a set of algorithms which are modifications to neural networks, and it's a type of algorithm which modifications to neural network can make the model do automated feature extraction plus job of classification or regression. Right, the difference between deep learning and machine learning is, in machine learning usually you have to do manual feature extraction and manual feature engineering, whereas in case of deep learning you have to do you don't have to do manual feature extraction. We can make use of the algorithm of deep learning, and it does automated feature extraction. Right, the technical differences, if I had to talk about, the key difference which makes deep learning algorithm very different from machine learning is this one. In ML, you have to try out different features and classifiers to achieve best result, where the algorithm in case of deep learning learns the features and the classifiers both automatically. Right, and so most researchers do not use deep learning for image processing. They use deep learning for computer vision. So you should not call it image processing, you should call it computer vision. And in fact, they also use it for NLP as well. And in both the cases, you deal with unstructured data. So the image, video, text, and audio are part of unstructured data. And it is difficult, complex to perform feature engineering or feature extraction with unstructured data. And that's where they prefer using deep learning. Right. And the performance of deep learning algorithms is better compared to that. ML algorithms give slightly less performance. Deep learning algorithms are faster to train, whereas, machine learning algorithms are faster to train. Deep learning algorithms are more expensive. Machine learning algorithms always give good result with small data set, whereas deep learning algorithms require very large data sets, right? So yeah, whenever you deal with unstructured data, that's where feature engineering becomes very difficult and complex to achieve. And this is a situation where a machine learning algorithm may not be suitable to achieve the good results, and deep learning algorithms gives better performance in such situations, right? And yeah, that's an actual idea. So Relu is not an activation function only in CNN, but it is also in almost every neural network. Whenever you work with any neural network on a hidden layer, we always prefer using Relu as an activation function. Well, so that's the idea about it, right? So we're going to talk about the most popular deep learning algorithms. So the typical applications of deep learning include examples like self-driving car, or idiom rejecting counterfeit notes, or smartphone app giving the instant translation of street sign. And another example of applications of deep learning could be you feed this image as input, and you get this thing as output. You feed this image as input, you get this thing as output, right? So that's something that a deep learning algorithm or a set of algorithms actually can do altogether, right? Yeah, so that's an actual idea about it. So let's talk about the talking about computational resources. Deep learning algorithms require GPU computing to train, so you need to have GPU based hardware to train the model, and to train that model, because without GPU based hardware it becomes very slow to train such models. And for prediction process you can still use CPU based hardware. We also have third option of inferring to cloud based hardware, where we get GPU pre-installed and configured on cloud, and those are more economic to use and train the model. You get such free infrastructure available from Google Colab as well. That's an actual idea about computational resources required for deep learning. So deep learning algorithms need high-end computational, and you can say infrastructure, and just to make them able to train the network, the faster the model faster, and without impacting the hardware quality, you can say, or maybe the health of the hardware. Okay, so yep, that's nutshell idea about it, right? The understanding of computational resources. Okay, and yeah, so now let's talk about the understanding of neural networks. So what exactly happens when it comes to deep learning? So deep learning algorithms are actually modifications to multiple modifications to neural networks. You can think of this as a very sample neural network. A modification to this could be deep forward neural network, which is where you have more than 2 hidden layers. If I have output feedback as input, this is a recurrent neural network. A modification to that with a memory cell is Lstm. A modification to that is GRU. We also have unsupervised learning algorithms of deep learning, which is autoencoders used for dimensional reduction, variational autoencoders used for pattern generation, deionizing autoencoders used for removing noise from images, sparse autoencoders used for recommendation and predictions as well. We have a lot of other variations of this, like Markov chain models or Hopfield networks used for unsupervised learning pattern recognition. Boltzmann machines or rested Boltzmann machines are used for recommendation engines. The one that we are interested into is convolution neural networks, and deconvolution used widely for the image based applications like image classification or image generation or segmentation of image objects, right? For many of these applications we use it. Modifications to that is again GAN. We have generative or fake videos. You might have heard of such things. Those are contributed by GANs, right? And then a lot of other variants of neural networks, not very having commercial applications, but yes, are research applications they have. But the most popular neural networks that are widely used in commercial applications today in industry are 3, which are deep neural networks, convolutional neural networks, and recurrent neural networks. In fact, instead of recurrent, the most popular are Lstm. So a variant of recurrent. Lstms are very widely used in commercial applications. So these are neural networks which are very widely used in the commercial applications, right? And the focus that we are interested into, the topic that we are interested into is convolutional neural networks, right? CNNs. So let's talk about now the understanding of CNN and what exactly it is and what it does, what do we do with it. If we go. So you can talk about the understanding of what exactly is CNN and what it is doing, and what we can achieve with it, and how does it works in general. So convolution neural networks very widely used for image related tasks like image classification, object detection, object localization. A lot of variations to this are achieved by convolutional neural networks or convolutions, right? So almost all kind of tasks of computer vision can be achieved with the help of convolutional networks, right? So typical tasks include classification. In classification, you have single class, or you can say single label classification. In fact, I should not call it single class, single label classification. Or I should write it again. So you see, one of the tasks is classification that you solve with images. In that you have two, which is multi-label, which is what we also call it is image tagging as well. You have single label. In single label, again, you have two class classification and multi-class classification. Then you have the the other task of localization. In localization, you have one object, which you call it as object localization. And for multiple objects, we call it object detection. We have third task, which we call it as a very popular task, segmentation, which is what we call as Scalar segmentation. These are three different categories of tasks which are usually solved under computer vision with the help of convolution nets. Right, so that's nutshell idea. And the one that we can talk about, single label multi-class classification problem, is what we're going to be actually working with. Right, so this is what we're going to be working with in this today's session. Classification tasks, single label image multi-class, single label multi-class image classification. Right, so that's what we're going to be looking at, a practical example of this. There's a question: is GNN technology related to deep neural networks? Well, GNN is actually built on the top of neural networks, convolutional neural networks. So generative adversarial networks are actually neural networks, built on the top of convolutional neural networks. In fact, right? So there is a CNN. There are two CNNs combined, and that's how a GNN is created. What is the difference between GNN and variational autoencoders? Where variational autoencoders also generate the output, and even the GNNs also generate the output of fake images or fake pictures. But VAEs are not as powerful as GNNs. In VAEs, you don't have two networks competing with each other, whereas in GNNs, we have two networks which are like, you can say, which are like the decoders and possibly you can say discriminators and generators competing with each other. That's the GN architecture. We don't have separate networks which are acting as discriminator or generator in VAE variational autoencoders. Right. So that's an initial difference. Okay, so I hope that answers the question. So well, we talk about, we are more interested at the moment in classification segment. So let's understand the idea of GN, how Rcnn for curved text extraction is used. Well, so Rcnn is a region-based CNN, and it is used to do object detection. And that's where it falls under this bucket of object detection. And it uses an approach for a region proportion layer to propose the regions in which an object or text may be present based on the segmentation tasks. And Then for those proposed regions, we feed those. Once we finish the CNN, we can talk about Rcnn if we have sufficient time, right? So if we have any question which is related to the current topic, I would encourage at the moment, if you think that there is some question which is a bit different but related, we can discuss that in more detail as well at the end of the session, right? So yeah, multi-feature extraction is like extracting multiple features. That's what the convolution segment does over here, right? So once we understand convolution segment, that is what multi-feature extraction we do. So yes, everyone, the features are, you can say that these are different. You can say that in a human face, let's say an eye could be a feature, right? Nose could be a feature, possibly lips could be a feature, ears could be a feature as well. So the job of CNNs is to extract the features automatically and then to able to learn from those features. Let's understand how does it works. Right, so in nutshell, the idea of CNN is composed of two things, 1 and 2. This job, this segment does the job of feature detection, and this segment does the job of classification. Let's understand this in more detail here. So CNN actually is composed of two things. First network, you can say that one network does the job of feature detection and the other network does the job of classification. The feature detection network takes the data or takes the image, extracts the best features, and those base features are then fed to the classification segment, which learns from those features and does the job of classification, or you can say the job of regression, or maybe whatever the job for which we have programmed it. In a nutshell, it's always, most of the times, it's classification. Right, now in what this second segment, which is the classification segment, it does the same job of dense layers, which we call it weighted sum activation function. So each neuron here, each neuron in classification is connected to each neuron in next layer, and they do the job of weighted sum activation function. Weighted sum activation function. That's what this classification layers actually do, right? So this is nothing new over here, but the new part is the feature detection segment. So we have convolution, we have Relu, and pooling. The three steps which actually help here are helping here. In a way to detect features are convolution, Relu, and pooling. Convolution, Relu, pooling, convolution, Relu, pooling. So convolution, Relu, and pooling are the three steps which are contributing to one unit of feature detection, right? And we can such have multiple units of feature detection, right? And yeah, that's a nutshell idea. So in order to understand that how this part of the network works, we need to understand the idea of what is convolution, what is Relu, and what is pooling. Another is like what is, again, like, same thing can be repeated, convolution, Relu, and pooling. So we need to understand specifically here what is convolution, what is Relu, and what is pooling. That's what constitute the idea of feature detection unit. And then we have the other unit, which is classification unit, right? And yeah, that's nutshell idea. So in classification, so once the feature detection works and we got the extracted features, in classification, we're going to be processing those features by the network, which is going to be composed of weighted sum activation function. Weighted sum activation function. We call them dense neurons or fully connected layers, right? So yeah, this is a nutshell idea. So in order to understand the working of CNN, we need to understand the idea of convolution, Relu, and pooling. Convolution, Relu, and pooling. Once you understand these three key things, that will help us to understand what exactly the feature detection segment does and how does it works, how does it extracts features out of it, right? So that's something that we'll be able to understand in this case. So now we're going to be talking about these three steps one by one. So first we'll understand convolution, we'll then understand Relu, and then we'll understand pooling. Once you understand these three things, we'll have idea of how feature detection actually works, right? So let me know if you're good so far. Any questions we have? There's a question. So can replace CNN applications with GN for solve more complex problem? No, both are different things. GN do different jobs, CNN do different jobs, right? So both are very different things. So if you learn about CNN and you learn about GN, you will have more understanding of how different they are and what they can do, right? So maybe understanding this might help you to understand what is CNN, and maybe similar other stuff might help you to understand what is GN. So CNN and GN are two different things, and they are used to solve two different types of problems. Right, so CNN applications cannot be replaced by GNN. All right, so yeah, that's nutshell idea. Okay, so here we go, and here we go, and let's talk about it, right? So we can talk about the idea of how convolution, ReLU, and pooling actually work, right? So let's understand that. So this is an example of convolution, how convolution actually works. In order to have more fair idea on this, let's take an example here. Now there are multiple approaches to convolution actually, and we're going to look at one of the simplistic approach of convolution, but they are even more approach to convolution, I would say, right? And yeah, so we're going to look at one of the very simplistic approach. So let's say that we have one of the image, which is here. And you know, this is sort of having an object, which is, let's say, X. And we have the corresponding pixel values. So let's say we have corresponding pixel values. And we have a feature map as well, right? So the corresponding pixel values we have, which are let's say represented like this. And we have corresponding feature maps. Okay, so let's say that this is the image, the original image. This is also the image, right? Let's say we can write the values of pixels here. And what we do in the process of convolution. So we're talking about the process of convolution. We take a filter here and we generate something called a feature map, right? And that's the nutshell idea, right? And now what we do is, so let's say that, you know, this is representing the image. So we can say that wherever there's a white color, we'll say 1, 1, 1, 1. White color is 1, 1, 1, 1. And let's say wherever there's a more of a black color, we'll say 0, 0, 0, 0, 0, 0. A very simple mapping, but you know, this could have been different, the values of pixels, because usually they range between 0 to 255, right? So let's say a very binary image. We have a very simple binary image, which is like composed of 0 and 1. And what we do in the process of convolution is we take a filter. Let's say the value filter is like 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. It could have been anything else as well, right? So what we do in the process of convolution is, in the process of convolution, we simply try to map the filter. We simply try to map the filter with the image. We simply try to map the filter with the image. We simply try to map the filter, you know, with the image. Right? We try to map the filter with the image and compare the values. So when you try to compare the values, you might say that, well, the first value of the filter multiplied with the first value, generally there's a multiplication, but let's say take another example to have an understanding of how does it logically affects, right? So the multiplication actually does the mapping. So you can say 1 matches with 1. So we're going to say +1 wherever there's a match. 0 matches with 0, 0 matches with 0. So we're going to say +1, +1, +1 for every match. 0 with 0 matching, 1 with 1 matching, 0 with 0 matching. So second row is matching the complete second row. So we're going to say 3 match +1, +1, +1. Third row, 0 matching with 0, 0 matching with 0, 1 matching with 1. So we're going to say +1, +1, +1. Divide by the value count 9. So you can say 9 by 9 is going to be 1. So you can say the map of this filter on this corner of the image is 1. So we're going to represent that by 1. Then we're going to simply rotate this, a rectangle. And now we're going to do the mapping here, right? So now we're going to do the mapping here. Now we're going to do the comparison here, right? one shift left like that. So we do comparison. This 0 doesn't match with 1, so we'll say -1. This 0 matches, this 0 matches, so +1, +1, +1, +1. Here 1 0 1 0 1 0, no match in the second row, so we'll say -1 -1 -1. Third row, it is 0 1 0. Here we have 0 0 1, right? So you can say that first 0 matches, second and third doesn't match. So +1 -1 -1. So we have total 3 2 5 and 6 -1. That is, you can say -3 by 9, which is, you can say -0.33. So we'll say here it is -0.33. Similarly, we'll again shift it left and then try to map it here. Right, so you can say we'll try to map it here. And we'll then do the calculation. So you can say 0 0 1 is going to be -1 +1 -1. Second row, +1 +1 +1. Third row, -1 +1 -1. Right, so we have total 1 2 3 4 minuses. You can say 1 by 9, which is 0.1. So the map here is 0.1, like that. It might, if there would be more rows, you can say we'll get some value here as well, maybe 0.4 or 0.3. And then we shift it down. So we then shift it down like that and do the mapping here. Now the idea is that more the filter is going to match, we're going to get higher positive value. Slightly match, slightly positive value. Mismatch, negative value. So if it is higher mismatch, I might get 0.8. If it is very slight mismatch, -0.3. If it is slightly match, we'll get 0.04 or 0.3 or 0.2. If it is very much match, we may get 0.9 or 0.8 or 0.7. If it is mismatch, -0.3. Slightly match, 0.24. Slightly match, 0.3. Very high mismatch, -0.6. So we may get different values according to how much that filter is mapping there or matching there in the part of image, and how much it is not matching. And that's how we generate the feature map. Right. So the feature map is the output of the convolution process applied with the filter on the image. It's an output of convolution between the filter and the image. Right. So yeah, that's more of nutshell idea about how the convolution works out. Right. Right. So we got the feature map generated here. Right. And you can say the feature map simply represents the matching of how much filter is matching with the image. In general, while programming, we do not decide the values of filters. We simply decide the count of filters and the size of filters. And the values of filters are considered as weights of the neural network, which will be trained, which will be updated when we train the neural network. And at the end of the day, we get the feature map. So if you talk about any standard image, let's say that if I take another image over here, which could be possibly, let's say if I take this image. So in this image, or in this particular photograph, or maybe if I take another one, in this photograph, let's say, let's say if my filter is, if the filter is representing I, right? So possibly if I just, copy this. So you can see that here, if the filter is representing, if the filter we have is representing I, so mostly here we'll get all the negative values. We'll get negative values, right? Because it's a mismatch, right? If the filter is representing I, if I have filter, which is representing, if I have filter F and that is representing I. So on most of the locations, I'll get negative values. Only I'll get a very high positive value here. I'll get a very high positive value here. I'll get slightly positive value because the lips also look quite similar to I. I may get slightly positive value on the button of shirt possibly, or t-shirt, or maybe some other positive value somewhere else as well, right? So these are the positions where I might get possibly higher positive values, and rest of all the positions will get negative values, right? As an output of the convolution process, right? So this is the convolution process. In convolution process, a filter is mapped on the whole image. It rotates through the whole image and generates a feature map, right? as I said again, we do not decide the values of filter. We start with random values of filter. While we train the neural network, the gradient descent process makes the filter get the best values. And at the end of the training process, the filters attain the features of the neural network, right? And we decide the count of filters and the size of filters as well, right? So it could be 3 by 3 or 5 by 5 or 7 by 7. That's what we decide, the count and the size of filters, right? This is a typical example of convolution you can see, right? So feature detection is the three-step process: convolution, ReLU, and pooling. In this case, you can see that we have extra taken, if I take the convolution process, so you see here, it rotates with a gap of 2, right? So this gap is called a stride. So here the strides is 2. Strides is the number of columns it is shifting, right? Which is number of shifts by filter is what you call a stride. And then if I do keep on doing this out, it may happen that the corner pixels are not much covered up. So we have added a layer of 0. You can see a layer of 0 on here, which we call as padding. So this is padding. Padding is addition layer of 0 on top, left, right, and of the image. Top, left, right, bottom, like that of the image. That's what we call padding. So here padding is 1 and stride is 2. So this is image. These are not 3 images. This is only 1 image. This is the red part of the image. This is the this is the red part of the image. This is the green part of the image, and this is the blue part. 3 matrices, you see, 2, 1, and 0. And this is filter F1. This is filter F2. This is red part of the filter, green part of the filter, and blue part of the filter, RGB, R, G, and B. A filter will also have bias, because a filter is actually essentially a weight. And this is where we get the feature map FM1 and the feature map FM2. Okay, there's a question. Yeah, deep learning being resource intensive, it can be supervised to learn. Yes, I mean, whether it is if it is about type of algorithm, whether it is not or supervised or unsupervised, you can say it depends on the problem you're trying to solve. CNNs are supervised learning algorithms, and it is very much resource intensive, right? So in a lot of cases, we kind of put triggers where the learning process is finished, and then we go ahead and evaluate the result, right? Every filter actually learns, you can say, yeah, that's correct answer from Santosh. So why do padding? To get the corner values, to care of corner values. For example, if I don't do padding, you see, if we are doing the process of convolution, so you see this corner value is only taken 1 time, but you see the middle value will be considered 3 times or 4 times, right? So the model or the convolution process will learn a lot from the central part of the image, but it will ignore the corner part of the image, right? So by doing a padding, adding an extra row, an extra column, the model very well learns the all part of the image, right? So that's the understanding of the why do we need padding in general, right? So the to take care of the corner values pixels, right? So that's where we need padding, right? So here you can see the padding of 1 is added over here. There's a question, why to use multiple number of filters? Each filter actually represent 1 feature. Now in the human face recognition, you can say that there might be multiple filters, features, eyes, nose, ears. Each of these are actually 1 feature. So each filter learns 1 feature. As many filters that you use, that much more features your neural network is going to learn. So there are 4 essential hyperparameters, which is first, number of filters. Second, size of filters. Third, padding. And 4th, strides. These are 4 very important hyperparameters of convolution process, and you don't want to control the values of each of these 4 hyperparameters and tune them. There is no way to calculate them, but yes, generally there is a lesser impact of these 2. So you may only want to optimize this at the higher level just to maybe reach out the standard size of the image or possibly standard size of feature. But most of this is more often tuned hyperparameters and more impacting hyperparameters. Right? So number of filters, size of filters, padding and strides are all hyperparameters, right? And there's no criteria for choosing stride, but yeah, there's a logic behind that. The logic is if you choose higher strides, you can say very small or low level features might be, or complex features, small complex features might be missed out. If you use lower value of stride, it may be computationally more expensive. So lower the value of stride, computationally more expensive. Higher the value of stride, computationally less expensive. Lower the value of stride, you may lead to overfitting, but also the model will learn complex features as well. Higher the value of stride, you may lead to underfitting, but also the model will skip the complex features and learn only important features. Now, let's say if I talk about two situations. One is the traffic sign classification, in which you have to learn from traffic sign data, right? So for example, if I have to give an example, let's say, if I give an example of, let's say, traffic signs. And we have multiple pictures of traffic signs. So if I have to train the algorithm to detect traffic signs, now in traffic signs, do we have more complex features? You might say, no, we don't have more complex features. It's simple features. So even if I use higher value of stride, the algorithm is though going to be sufficiently able to learn the patterns and the the features of the traffic signs, right? The higher value features are logically good. It's not a big challenge. Sorry, higher value strides. Higher value stride is not a big problem, and high value stride will do the job because the features are not very complex. They are simple. But if you look at the idea of human faces, right? So if you look at the idea of human faces, there are multiple small complex features. A high value stride might lead to loss of complex and small features. So you may want to use lower value stride for this. So the stride, lower value stride leads to more computational cost. Higher value stride leads to lesser complication cost. But at the same time, you want to, you want to incorporate the complexity as well. I mean, I would say precision of features which is being learned. Right. So that's the answer. What is pooling on CNN? We'll talk about that. We'll talk about that. Is there any? There are three inputs, the three filters twice, but only two outputs. Yeah. So it depends on what is the architecture of convolution you have taken. So this is the output of convolution 2D. So in convolution 2D, we don't take care about colors. We only take care about features, shapes of objects, right? There are not three inputs. These are only one input. So there is only one input image. It just, for that image, there are RGB, three different matrices. So each image, color image, is always composed of three matrices: red matrix, green matrix, blue matrix. The combination of RGB creates almost every color in the real world. And we have two filters here. And for each filter, we have one feature map. Right. So each filter is also three-dimensional. So it has RGB, RGB like that. So there is only one input image, two filters, and corresponding two feature maps. So yeah, that's nutshell idea. Okay. So this was about the idea of convolution. Let's talk about the next step, which is ReLU. And then we'll talk about pooling as well. As we already know, the ReLU is activation function fx equals x greater than 0, and 0 for x less than equal to 0. That means ReLU will do what? It will make wherever there is a negative value in the feature map, it will reset all the negative values to 0. You see what ReLU is doing? Wherever there is a negative value in the feature map, it is simply converting the negative values to 0 and keeping the positive values as it is. That's what ReLU is helping us to achieve here. It's simply converting negatives to 0 and keeping the positive values as it is. Now, that means what will happen is, now if you talk in this image, in this case, wherever we got negative values of the feature map, because of ReLU, the whole portion will become 0. That means black in color, and only the eyes, only the real part of the eyes will remain as it is. This part will remain as it is, and this part will remain as it is. So only the very important features, which are very much mapping with the filter and slightly matching with the filters, will remain, and whatever is mismatching will completely be reset to 0. That means the t-shirt, the background, ears, nose will become black in color, as that's going to become 0. Right? Only the real eyes are going to be appearing, and on the lips, which look like eye, are going to be appearing possibly. So slightly matching features will appear. That will happen at the step of ReLU. So Relu will remove the values which are unwanted, or the part of the image which is not relevant, right? And that's the job Relu does. Right? So it is simply resetting the negative values in the feature map to 0. That means wherever the filter was mismatching, that will be suppressed to 0. Next step is pooling, which is super interesting and very important. So pooling is like, there are multiple approaches to pooling. We're talking about a very simplistic approach, which is max pooling. What it does is, so max pooling simply pools maximum value. So we select a pool size. Pool size is a hyperparameter, which is, let's say, 2 by 2. So I select a pool size 2 by 2, which is usually this is a pool size. So from this 2 by 2 window, we'll pull the maximum value. The maximum value is here 6. So we'll pull 6 and put 6 and say that 6 represents all the 4 values. Similarly here, the maximum value is 8. We'll say 8 represents the all 4 value. 4 maximum values. So in this 4, the 4 is maximum value. We'll say 4 represents the maximum value, the all 4 values. 3 is maximum, so we'll say 3 represents all 4 values. So you can say that the image or feature map, which was 4 by 4, now got reduced to 2 by 2. This is what pooling does, right? So it reduces. Pooling is also called as, we also call it as downsampling as well. We also call pooling as downsampling. It downsamples the image and drop out slightly positive values. So whatever is worth 0 and whatever was slightly positive value will be dropped out and will be kept as highest positive value will be kept as it is. So if you again look at the picture of human face here, convolution will lead to get the negative or positive values, negative values or positive values, negative values or positive values. Relu will make all the negative values go off. All the negative values will become 0. Pooling will remove all the slightly positive value. Now you see these are going to be highly positive. These are going to be highly positive. And this is going to be slightly positive. You know, this is going to be slightly positive. When you apply pooling, out of slightly positive, we can just pick out the highly positive. That means we have dropped which were somewhat matching features, which could be the lips, which could be the button of the shirt possibly, and those are, you know, dropped out. That's where at the end of the pooling, you will have only eyes left in the image. That's how eyes are extracted, right? This is what you call as feature extraction. This is how the feature extraction is done. So in the human, you know, in the image frame, even if my photograph is here or my face is here, or wherever the human face is, you know, it's going to be able to identify the 3 steps altogether, are going to be able to identify where the eyes are, or whether there's an eye or not. Right. So convolution simply generates the feature map, which with positive, negative values. Relu is suppressing the negative values to 0, and pooling is just picking up the maximum values and taking that, you know, as the best features. Right. So it is doing the job of downsampling, dropping out slightly relevant or slightly positive values of feature maps. 3 steps altogether helps in doing feature detection. We can repeat the 3 steps multiple times. This could be an example of how does it works possibly, right? So initially, the combination of convolution, Relu, and pooling helps in detecting low-level features like edges, right? So these are called as low-level features, right? So we call them as, these are called as low-level features, and this is called as high-level features. Now, upsampling is different than downsampling. Upsampling is reverse of downsampling. The way we reduce the size of the feature, you know, to half in downsampling, upsampling increases it, right? So it is reverse of it. So yes, this is how you see, you know, this composition of convolution and pooling helps in learning different features. How you know, low-level and high-level features can help in recognizing possibly 9. Right? This is just for 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So yeah, that's the idea. Yes, we can initialize the kernel values in Keras, you know, by there are some hyperparameters via which we can do that. We can even control the randomness and the values which are generating randomness as well. We can define a template of values and we can map them up. So one of the way is like you can generate you can use a neural network and save the weights of it and load the weights in a neural network developed in Keras, and that's how you initialize the values of kernel values of in Keras, kernel values of the weights or filters in Keras, right? So whenever you load any saved weights to the neural network, that's how you're initializing the initial values of weights in case of Keras. And Keras allows that option to load is the saved weights. So you can save your weights that you'd want to, or the values of filters, kernel values that you would want to load, as a weight file, and then you can load it. Okay, so that's the idea, right? And yeah, this is this is how it works. In case of face recognition, this would work like this, right? So initially, the job of convolution relevant pooling is going to help to detect low-level features like edges, then a little high-level features like ears, eyes, nose, and then very high-level features like the facial structures and all, right? These are very high-level features that it detects. That's a nutshell idea about it. That's a nutshell idea of understanding how does it works, and how it helps in extracting features to learn from. So this is the idea about how exactly the logic of convolution neural network works, right? So these are the 3 steps which help in doing feature detection, and then once features are detected, we do the job of classification, right? So convolution relevant pooling help in doing feature detection. Convolution relevant pooling, we can use multiple units of them, and then extracted features we can feed it to a classification network which can take the extracted features and do the job of classification out of it, right? Which could classify that as maybe A or B, happy or sad, or something like that. That's an nutshell idea about it. I hope you're good. Is there any online tool that do this, or we have to write programmatically? Well, there are online tools which can do this, but we're going to look at programmatically as well. So if I were to share an example of online tool which can do this, I can do that now, and we can take an example. We can take an example quickly, right? But yeah, so we can now look at the programming implementation. But before, in a nutshell, I'm going to show a quick idea of online tool which can do this, at least for teaching purposes. You can use this out. So you can use a tool called Teachable Machine Learning. That's a super popular tool, and even it's a free tool to use to teach at least, all right? And to show example of it, how does it works? All right, so not teachable.com, it is Teachable Machine with Google. So that's an example here. Let's go ahead and see that out. So if you're teaching, you are teaching neural networks, there are a few of the tools which can help you out to ease out the teaching process. That could be image project, let's say on Teachable. So I can, let's say, train a model here to do the job of classification. So I'll have to switch off my camera for showing this exercise, right? Because we're going to be using our camera here. So let's say that, let's say that we would want to build a neural network here, or maybe a model which can do the job of classification between 2 objects. And so first we can capture data, and then we can do the job of classification here, right? So let's take an example here. So let's say I want to do classification between 2 things. One is the AC remote, and the other is possibly the water bottle. So I want the model to be able to classify between these 2. We can add more class as well, right? So first we need to capture some images, and we're going to do that here. So I'm going to switch on the webcam. So you can see that this is the AC remote we have. So I'm going to hold to record some pictures. So we have a few pictures saved of AC remote. So around 100 and 200 pictures, let's say we have for AC remote. Now we want to save some pictures for water bottles, right? So we have water bottle, right? So there's a water bottle I have, and we're going to save some pictures of water bottle, right? So record some pictures of water bottle. So around similar number of pictures helps a lot. You should take different pictures with different structures like that. And we have around now, let's say, 219 pictures of water bottle and 206 pictures of this. So now you would want to train a model, a neural network model, which can learn from this. And here we go, train the model. You can do a lot of other customization to the model in a way to control the value of learning rate and the number of iterations, and a lot of these factors can be controlled out. I wanted to show this advanced tab, and that's where you can do this. So you can see it is going for 50 epochs. You can change the epochs, batch size, learning rate. Other defaults you can change under the hood, which could be number of neurons and the number of layers in the neural network. A lot of these could be changed. Accuracy per class, accuracy per epoch, right? So you can see this out as well. So this is how the the neural network is changing out. The accuracy is changing in general. And finally, we have a trained model available. So if I put a AC remote here, you can see that it's showing this AC remote for this, but when I change it, it's showing a water bottle for this, the probability of this, and AC remote, a water bottle, right? So it is doing the job of classification. This is an example of two-class classification. You see, it is classifying the current image, whether it is a water bottle or it is an AC remote, right? So it says this is AC remote and this is water bottle, right? So it does the job, right? This is a simple example of to train it, but you can also use this in application as well. But this is a simple example to understand, how does it works. In case you are teaching, to students and you want to even teach them in more detailed way, there's also another very popular tool, which is playground.tensorflow.org, which is a very popular tool. And this is where you can teach them about the understanding of neural networks and how does it impact the concept of overfitting and underfitting. So you can see that here we have the epochs, right? So we have two features, x1, x2. I have selected this data. We have options of 4 data sets. You would want to explore this. There's a linear model. So for a linear model, this is a linear data. You see that blue and orange dots are two classes. They are linearly separable. So even without the help of any hidden layer neuron, I can still kind of generate the output. So we have two hidden layers. I'm going to remove that, right? So no hidden layers at the moment. Without hidden layer also, if I train this as this is a linear data, you see I'm able to identify the classifier. It is able to learn that, and it is able to do the classification without the presence of any hidden layer, because the data is linearly separated, right? So in more of these epochs, 400 epochs, we are able to get a good classifier without any hidden layer. But if it would have been a non-linear data like this, we cannot get good classifier and the error will be higher. You can see that loss on trained data and test data is higher. We cannot get a good classifier without the help of hidden layer because it's a non-linear pattern. The moment you add a hidden layer with two neurons, the network becomes slightly nonlinear, and that's where it will be able to identify a few good patterns. You can see that. Still, it is not perfect, right? You would want to make it more nonlinear. Now you see this is very interesting and important. We added two hidden neurons, and it is nothing but two linear models at the moment. You can see, right? So with two hidden neurons, the neural network is actually learning two linear patterns, right? You see there are two linear patterns it is learning like that. So, and that's why it is learning nonlinear pattern on a whole. If I increase the number of hidden neurons furthermore, it will learn even more nonlinear patterns and solve more complex problem effectively, as you can see that. Right, so now it is able to solve nonlinear problem and more effectively, right? That's an actual idea about it, right? You can do a lot of other customization here. I can add one more hidden layer. If I keep on adding more and more hidden layer, it may also lead to overfitting as well, right? So even that sort of logic can be also attained here. Right, that's an actual idea about it, right? So if you put a little bit of noisy data, you see in this case it can kind of underfit a little. This is more noisy. But presence of multiple hidden layers with multiple neurons might lead to a little good model, more complex model. This might become computationally more expensive, but at the same time, it will be easy for neural network to be able to learn from that. There's even highly complex data, as you can see. Right. Maybe for this, you can get even better performance. Well, these are a few tools you can use for teaching. Let's go at the moment. Here we go, and we're going to be working with a practical example with Python on the idea of convolution neural networks. Well, the data set that we're going to be using up in this case is the data set of, let's say, we have a few images of dogs. So we have around, let's say, 200 images of dogs, 200 pictures of dogs we have, right? So these are different pictures. All the pictures are of different size. As you can see that all the pictures are of different size. And they have different complexity as well. We have 200 pictures of horses. 200 pictures of horses, and 200 pictures of humans as well. The data is a little complex because in some pictures of humans you have horses. You can see that in some pictures of humans you have horses and humans both, right? So it's a very complex data, a little actually, right? So the objective is to train a model which can be, which should be able to learn from this data, and for any new photograph, it should be able to identify whether that has a human or a horse or a dog, right? So we want to do a 3-class classification problem, identify whether an image has a dog or an image has a horse, right? Or it has a human, in it, right? But then there are a lot of complexities, as we know that in a lot of human images they are horse, in a lot of dog images they are humans as well, right? So in a lot of dog images you'll find that they are humans, which makes it a little difficult to learn that how to differentiate between an image, right? Whether it is a horse or human like that. So if I show you that, it could be possibly, yeah, you can see this image, you have human and dog both. This image you have human and dog both. This image you have human and dog both, right? These are different challenges that we have with this, right? When that's going to be stopping us from getting good performance. Well, so this is the data that we have, and we want to work with this data to develop a solution on the top of this, right? Here we go, and let's do that. So our objective is to develop a multi-class classifier which can learn from this, and for any new image it should be able to do a prediction, or whether that image is possibly a human or horse or a dog. So this is it. So I can go to new option, new notebook. I can name this as RKGIT. Right now, whenever you start with this, you should always change the runtime in case you're using TensorFlow. So in runtime, I'm changing the hardware accelerator to GPU. That will make me achieve this job faster, help me with this faster. So first I need to get data in the collab. For that, I'm going to be downloading data from my GitHub. So I already stored this data on the GitHub repository. I'm going to downloading that here. And then I need to unzip it. So I'm going to say unzip image_data.zip. Right, so once it is downloaded, I'm going to be able to unzip it. We're going to be loading a few packages, which could be NumPy, import NumPy as NP, import matplotlib.pyplot as PLT, import matplotlib.image as IM. Possibly we're going to be also importing up from TensorFlow.keras will import image as IM as IM. We're going to be removing this. We don't need this then. And from TensorFlow.keras.utils will import toCategorical and also plot model. From TensorFlow .keras will import models and layers. Right, so this is where we have loaded the important packages, and here we go. First task we'll do is to load data. So we got some error, NumPy, I did a typing error in NumPy. So first we can write a code for loading data, and from TensorFlow.keras.preprocessing. So first we can write a code for loading data. So we're going to say this is where we're doing uploading data, or maybe you can say this is more like a data set preparation. Okay, so we have, let's say, our main folder, which is where our data is present, that is image data /data. So if I look at, we also wanted to import one more library, that is import OS. So if you look at os.list_dir main folder, so in this case we have 3 folders which are dogs, humans, and horses, right? So we'll say that these are our folders, or maybe these are our names of the folders. So in main folder, we have 3 folders, dogs, human, and horses. In each of the folder, we have around 202 images of horses, 202 images of humans, and 202 images of dogs. We want to load them up. So for that, we'll define 2 empty lists first, X and Y. So X to store images, right? So this is to store images, and Y to store labels. So we'll do here for each folder in the names, we'll first get the file names. So we can say file names is os.listdir main folder plus we will say slash plus the folder. Once we have all the file names, right? So yeah, NumPy is used for mathematical computation. So we're going to be using that for a little bit of mathematics. We might need it to convert the list into array. So for that, NumPy is mostly used for mathematical computation. Matplotlib is for graphics, visualization, and also plot. TensorFlow is the main package from which we are using Keras. Image is going to be used to load images and resize them. Also, if needed, pre-process them. Two-categorical is to convert the label from normal format to one-hot encoded. Plot model is to plot the model. Models and layers we'll be using to do the modeling, which is where we will be using them for creating a neural network, programming the neural network. OS is for standard operating system related operations, like the way we used OS for getting the list of all file names from the main folder. Right, so that's nutshell idea, right? So we're going to be using more them up and we'll understand that what they are doing in general. There's a question, which algorithm will work well for complex images? Well, CNN works very well for complex images and are typically efficient to solve complex problems. Right, please explain the role of, yeah, so I have done that and I'll even keep on explaining more at the end as well. We can discuss that out, how have you used it. How can we process the EEG signal data set using CNN? Well, we can convert EEGs. First, we can plot the EEG signal in frequency domain. We can just export the frequency domain mapping of EEG signal as an image, and that we can process that using CNN, right? So this is a very popular approach to handle any audio signal as well, and also EEG signal as well. So plotting that into frequency domain, frequency graph of it, and then exporting that image to do the image classification. So we got the file names here, and for each file, now we'll do for each image name in the file names, we'll simply try to load the image. We'll say, or we'll say first path. Path of the image is main folder because it's going to be inside the main folder, plus slash plus the folder name plus slash. So we're just creating the path, plus image name. So we can simply load the image as im dot load image from the path, and we're going to mention target size. As all our images are of different size, we're going to resize all of them into, let's say, 250 by 250. So we're resizing all the images to 250 by 250. Finally, we can convert this into array. So im dot image underscore to array of img. And once we have converted that to array, we'll append that into list X. So we're storing all the images into X. Now we have to also know the label into Y. So we'll store the folder which contains the name of folder, horse, humans, or dog, into Y. Well, instead of storing the folder, we'll say y.append names.index of the folder. That means we'll store the index of the folder. That means 0 for horse, 1 for humans, and 2 for dogs. Right, once we are done with this part, so we got, say, folder not defined. That means I did somewhere error, folder, yeah, here, folder, and folder. So it says in this line, file names. Main folder is defined. Oh, here is the error. Okay, so we got data loaded. Let me convert X equals numpy dot array of X and Y equals np dot array of Y. So if you look at Y currently, Y is actually a set of values like 0, 1, 2, 0, 1, 2, 0, 1, 2. So all 0 for horse images, 1 for humans images and 2 for dogs images. Well, in order to get them one hot encoded, we would want to convert them into categorical format. That means get them one hot encoded. Right, so this will simply convert y into one hot encoded format. Now we can print x.shape and print y.shape. So this will convert x and y both into one hot encoded format. So finally, we have the data set ready. X is collection of 606 images. Each image is of shape 250 by 250 of 3 channels. That means they are color images. 3 represents R, G, and B color channels. Whereas we have labels, which is like 606 by 3, which is where 3 represents the please increase the zoom code. You want me to increase the size? I'm going to do that. Okay, so X is representing 606 images, each of shape 250 by 250 of 3 dimension. You can say that is 3 channels RGB. Y is the 606 labels of 3 objects, which is where 3 represents the number of objects, that is horses, humans, and dogs, right? So yeah, that's where we are done with the data set preparation. We have the X and Y, the data set ready to go ahead. There's a question, how can we process EEG signal? I have answered that. In any main advantage of using CNN, right? There are a lot of advantages. Just without using CNN, you have to do manual feature extraction, whereas CNN does automated feature extraction. So you don't have to manually extract the features. The algorithm itself will learn what features are important to be able to identify human or horse or dog. How can process a CSV file in CNN model? We can load that data and prepare just X and Y. You just need to have X and Y, the data set preparation. So based on the source of data, the process of data set preparation might differ. So at the end, the way we have X and Y, you need to also have X and Y based on whatever is the format of data that you have, whether it is CSV, whether it is Excel, whether it is SQL database table, or it is, non-SQL database or set of images, videos, audios. You just need to have your X set of features or set of data images, and Y, which is the label. Okay, I hope that answers the question, right? So the answer to the question, main advantages of CNN, again, a little bit of it, I would say. You see here in this image, the position or the part of the image which is important to identify dog is this one, right? Possibly you can say that there's a certain part of the image which is important to identify that this is dog, right? Which might be different from another one. I'm sorry, I just need to discard this, I guess. Yeah, so you see this part of the image is too important to identify dog, and that might change here. Only this part of the image is too important to identify dog. Whereas in this image, there's a different part of the image which is important to identify dog. There's different scales of dog, different sizes of dog, different features visible. Now the feature extraction of which part of the image to learn, which part of the image is important to identify it is dog, that is what we call feature extraction. CNNs do automated feature extractions. You don't have to tell that in this image what is background, which is not dog, and what is not background, which is dog. So you don't have to tell the CNN that, well, in this case, this table is not a dog, whereas this black color object is a dog. You don't have to tell the CNN that the grass and the road is not important to identify dog, and the central part is the important to identify the dog. You don't have to tell the CNN that the ground is not important here, or maybe the floor is not important here to identify a dog. It does automated feature extraction. Which features out of this image are important, which features are not important, it does the extraction of that automatically. That's a benefit of it. I hope that answers your question. How CNN knows which is the best feature? That's what the process of convolution, relu, and pooling. When you train the neural network, you'll have the layers of convolution, relu, and pooling. Convolution, relu, pooling is a feature detection unit, which is what helps the CNN to learn what are the best features and extract those best features to train the model. So initially, CNN doesn't know any features, right? So you just initialize the number of filters. Each filter is representing one feature, which CNN doesn't know what is that feature at the initial level. When you train your neural network with the help of data, the values of filters keeps on changing, and that's how CNN learns which features are most frequently available in all the images, and it learns to identify those features, and at the end of the training process, it retains the best features, right? So that's a nutshell idea of how does it works. I hope that answers your question. So now we're going to be going ahead to the task of modeling, I would say, right? So where we'll talk about building or I would say designing the CNN, right? That is convolutional neural networks. No, we have not programmed yet the CNN part. Now we're going to program the CNN part. So right now we have not programmed CNN, we just have loaded the data. We have only done data set preparation, right? So data set preparation is like we try to load the images and we store them into X and Y. So now we have X and Y. X is representing all the images, Y is representing all the labels. We just have done data set preparation. Now we are going to program the CNN part, right? So here we go. So first we'll start with creating a sequential model, right? Or maybe you may not want to create a sequential model. Let's go ahead without that and now write this layer. So we'll say layer 1 is input layer. So we'll say layers dot input, right? So layers is something that we imported. If you remember, we imported layers here, right? We imported layers on the top, right? So layers, and we imported here models and layers. So we're saying layers dot input, right? So layers dot input. So we have input layer as well, and we're going to be simply saying that let's say layers dot input layer, or maybe input only, and we can mention shape equals. So we have to mention the shape of each images. So each image is of shape 250 by 250 by 3. That's the shape of it. Then we'll say layer 2 equals. Now we're going to add, this is where you had the input layer. Now we're going to add the convolutional layer, right? So this is where we are programming the feature detection segment, the feature detection segment. We are programming the feature detection segment, and we'll also program the classification segment accordingly. We'll also program the classification segment. So right now we are into feature detection segment. So we'll say layer 2 equals layers dot convert 2D. So we'll say layers dot convert 2D, which is convolution 2D, and we'll pass here that we want filters. Let's say we want filters to be initially 16 filters or maybe 8 filters, and kernel size, which is, let's say, filter size. Kernel size is nothing but the filter size. And there was a question about kernel initializer. So you can see that there's one more hyperparameter in Keras, which is kernel initializer. So you can also pass the value of kernel initializer as well, right? We have kernel size, and we're going to mention kernel size as, let's say, 3 by 3. That means the filter size. We're going to finally mention the activation layer. So we can say activation is Relu. And we have to say layer 1 as an input to this, right? So whatever is the input, so this is connected to layer 1, like that cascading we are doing here. Similarly, now we're going to add the now we're going to add the max pooling layer, where we're going to say layer 3 is layers dot max pooling 2D. We can mention the pool size 2 by 2. So from 2 by 2 window, it's going to do in the pooling. This is where we had it, and we have to say here layer 2, which is the cascading. So we have to do like first layer, and that's input to layer 2, and layer 2 is input to layer 3, like that. So you have to pass the input layer here. Have we changed the setting of collab to? Yes, we have done that. We already changed the setting of collab to GPU. So this is where we have added one unit of feature detection: convolution, Relu, and pooling. Convolution, Relu, and pooling. We can add such multiple feature detection units, right? So we can kind of copy this and paste here, and just say that this is layer 4, and the input here would be, you can say layer 3, right? Similarly, this is going to be layer 5, and the input here we're going to be layer 4. We should always take increasing number of filters. So as we have taken 8 filters there, we can take 16 filters here, right? It's not about double. You can take any other ratio as well, but yeah, we should. It should always increase the number of filters in subsequent convolution units. So now we have this pooling layer. This is where we are done with the, let's say, feature detection. We can still add as many as convolution layer. It's not necessary to always add a pooling after convolution ReLU. You can also add 2 convolution ReLU in one pooling as well, right? So that's also a possibility. Now we're going to add a flatten layer. The job of flatten to convert the matrix to array, right? So for example, it can convert 5 by 5 matrix to a 1 by 25. So we're going to say layer 6 is layers dot flatten, and we can say here it is layer 5. That's where we added flatten layer. Now we are good to go ahead and shift to the idea of classification segment. To program the classification segment, so these are 2 different segments: feature detection in one segment, classification is other segment, right? In feature segment detection, we can simply extract features. We can add max pool, multiple convolution ReLU pooling, convolution ReLU pooling, like that, multiple layers. And now we are into classification segment, which is where we can say layer 7 is layers dot dense. We can add, now this is, let's say, hidden neuron. You can add as many as neurons you want. Let's say we're going to be adding here around 200 neurons, saying activation is ReLU, right? So 200 are units, that is neurons. And the output, the input to this is layer 6. We can add one more hidden layer. So this is, you can say, adding a hidden layer, right? Fully connected layer. So in classification, we add fully connected layers, which do the job of, yeah, I'll be, sharing this Python notebook as well. So which do the job of simply weighted sum plus activation function. They do this job. So yes, we can now go ahead and add finally the output layer. We can add one hidden layer. We can add multiple hidden layers as well. Finally, we'll say that, let's say we'll do adding the output layer. And we can say layer 8 equals layers dot dense. In output layer, the number of neurons depend on how many class classification problem you're trying to solve. As we are dealing with 3 class classification problem, which is humans, horses, and dogs. We have 3 classes, right? 3 things to identify: human, horses, and dogs. So we'll use 3 neurons in output layer. As it is 3 class classification problem, it is multi-class classification problem. So we will say activation is softmax, right? So for 3 class, or 3 classes like multi-class classification, so activation is softmax. So this is the whole idea of the neural network that we have built, right? Finally, you can say that instead of layer 8, we can also cascade this as layer 7. Instead of layer 8, I can also call it, you can say, output layer as well. Not a necessity, just a logical input. Or maybe I can say, this is layer 1. I can keep it layer 8 itself. It's fine. Right. Now, finally, we can build the model. Model equals models dot model. And we can mention inputs equals layer 1, comma, outputs equals layer 8. So layer 1 is input and layer 8 is output. That's where we are done with the model. This is where we are done with the modeling process. Now, finally, you can also see the model. So you can do plot model of model. This is our model we have programmed. It starts from input layer, then a convolution, max pooling, convolution, max pooling, flatten, dense, and finally one more dense. Right. This is the architecture of our model that we have designed. Now, once we are done with this part, we are happy with the model part process. We'll simply go ahead and compile. So this is where we are now starting off with the designing the model we are done with. We are going to be going ahead to compile and train the model. For 2-class softmax is powerful than Sigmoid. Well, 2-class Sigmoid is more preferred, computationally less expensive, and better to go for. So 2-class problem, both the approach are doable, softmax and Sigmoid both, but we always prefer Sigmoid for 2-class compared to softmax. Softmax is referred mainly for more than 2, that is multi-class classification. So compile the model. So we'll say model.compile. We'll use the hyperparameters loss function. So for softmax, the loss function is categorical cross entropy. For 2-class or sigmoid activation function, the loss function could have been binary cross entropy. For regression problem, it could have been MSE or RMSE. We'll also mention the optimizer. So optimizer is like we have to choose gradient descent. We'll choose Adam here, which is modification of gradient descent in which we don't have to tune the learning rate. And finally, we'll choose metrics equals accuracy. This is where we are trying to compile the model, right? And finally, we are going to go ahead and train the model. But to train, we may want to split our data into train set and test set as well. For that, we can say from sklearn.model selection, we can import train test split. And finally, we can say that xtrain, xtest, ytrain, ytest equals train test split x, y, test size equals 0.2. And in order to fix the randomness, we can say random state equals 5. This way we split our data into train set and test set. Finally, we can go ahead and train the model. Model.fit xtrain, ytrain. We can mention epochs is we want to train it for 20 epochs, let's say. Batch size, as we may not want to feed the whole data all at once, we may want to feed it in the batch of, let's say, 32. And we can say validation data. Validation data is xtest, ytest. That's our validation data. And let's go ahead and train the model. So this is where we are starting to train the model, all right? So batch size is the size of the number of images that we would want to pass in one go, right? So because of GPU selection, you can see that the training process is quite faster. And if you look at the performance analysis, the training accuracy has reached to 100%, but the validation accuracy, that means the test accuracy, has reached to only 68%. That means the model is heavily overfitting. The model has very well learned from the trained data, but it is not able to put that much good prediction performance on test data. As you can see that 100% accuracy on train, which is only 68% accuracy on test data, which is bad. So we don't have a good model in place, right? And that's where we can go ahead and do a little bit of more tuning on the model. So whenever you have overfitting, you can see that the model is more complex, and that's where we have challenges. If you look at the structure of model by using model.summary, so it gives us summary of model. We have around 5,936 parameters here. We are considering 200 out of them to train further. And this is the architecture of model, how our 250 by 250 image is getting reduced further, and going next. Now, in order to improve the performance further, you see we want to have a good model, which is like very overfitting model. It's having 100% accuracy on train, but only 68% accuracy on test. In order to even further understand where the model is failing, or maybe where the model is actually confused out, you can go ahead and analyze the confusion matrix on the test data, right? So for the test data, you can get ypred equals model.predict and you can get something like xtest. And finally, we can say the ypred. So it's simply, we have the 3 probabilities, right? And you want to consider the maximum probability. So we can say that ypred equals, or maybe ypred2 equals np.array of np.argmax of k for k in ypred. That's where we have ypred2, which is where the prediction is there. The model belongs to which particular observations, which particular class. Now from the ypred2, we would want to possibly, this is where the prediction we have. We would want to possibly compare this with ytest and check the performance of model, right? So we can say from sklearn dot model selection, or maybe metrics, import metrics, and we can see metrics dot confusion matrix of y-test comma y-pred. We may get a challenge here because it should be 0, 1. We may get an error over here. Right, so we need to also get the one label indicator for y-test. We can say y-test2 is again np.array of the same process. We can copy here. Just to convert into the same format. And this is where we have now the confusion matrix between y-test and y-pred. So you can see that here, this is the confusion matrix. If I have to better explain that, CM equals to this, and I can say import pandas as PD, and CM equals, or you can say PD dot data frame CM comma index equals names comma columns equals names. Right, so you can see that here, these are all the actual ones and these are all the prediction. 25 pictures which were of horses are predicted as horses. 6 pictures of horses predicted as humans. 7 pictures of horses predicted as dogs. 1 picture of human predicted as horse. 35 pictures of humans predicted as human. 5 pictures of human predicted as dog. The column shows the prediction, the row shows the training. 11 pictures, which is a very huge number, of dogs predicted as horses. So the model is confused between the dogs and horses. Right, so maximum confusion you can see the model is having between dogs and horses. It is not able to differentiate between dogs and horses, and then it is having confusion between dogs and humans, like that. Right, so there's a lot of lag between dogs and horses, as you can see over here, which we can again take into account and do the tuning of model accordingly to be able to improve the performance of model. Right, now in order to get the prediction for single image, you can, let's say that we have one image which could be possibly let's say X test. So if I look at X test, img equals maybe im dot load image of, or maybe img equals, let's say X test of 0. If you try to see that, plt dot im show img, this is the image that we have. Oh, I have to say dot as type int 32. So let's say this is the image we have, and we want to predict for this image whether it is human or horse or dog. So we can say that model dot predict img dot reshape into 1 by 250 by 250 by 3. And the prediction turns out to be 10 to the minus 11 probability for horses, 10 to the minus 1, which is for humans, and 10 to the minus 1 for, that's for, I guess, dogs, right? So it has slightly higher probability for, dogs in this case and less for humans. But yeah, those are on the wider range. You can say 0.8 for this third one. If I look at names to map it, so you can see that this is having 0.16 for humans, 0.83 for dogs, and 0.0000 for horses, like something like that. So that has a bad model. As we already know that the model is bad, it is not giving us good performance here. As we could see, the performance is very high on train, but it is not sufficiently that good on test data. We need to do the tuning of model to get the good performance. Yeah, but this is how you can, make a prediction for a single image. This is how we tried out making prediction for a single image. It's just the prediction is wrong because the performance of model is not that good. Okay, so that's a nutshell idea. That's a nutshell idea of how do we do this? How do we try to achieve this? Right. And what we can do is we can go back and do a bit of tuning to the model to improve the performance here. So we can go back and here do a little bit of more tuning to the model to improve the performance of the model. So first we can improve the feature detection segment. Maybe we can add more layers over here. So instead of, in order to just avoid the further addition, we'll say layer 4 here, or maybe we'll say layer 4 here. We'll simply give the same name. It's fine. It's okay to give the same name. All right, it's not a challenge. Okay, so we're adding more convolution layers. In fact, we added actually one more. We should add only 2. It's fine. And we're going to say here 32 neurons, in fact. Right. We can also add dropout optimization as well. So we can simply also do here, let's say layer k equals layers dot dropout with 0.2 and make layer 5 as input. And here instead of 5, we'll make it layer k as input. Right. So just adding some layers in between. And again, we plot the model. So the way now we have customized our outcome as we have first input, convolution, pooling, convolution, then pooling, and dropout, flatten, dense, and dense. If you check this performance of model, this might go a bit different. There's a question: how to determine unknown class using ANN? Well, that's what you were doing it, but only out of what we have trained the model. So if it is anything out of horse, humans, or dogs, we cannot use this model to identify that image or to predict that image, to recognize that image, right? So the prediction or classification problems are always supervised. That means you have to train the model first with the set of data, and then only you can do predictions with it. Now this model is very bad in terms. You can see that around 30% accuracy on train and 30% on test. It's even bad. So the changes that you have made were not successful or not that good enough to get good performance. We need to keep on doing some changes to be able to get better performance on this, right? But yeah, that's an actual idea. How do we do that? So this where, and again, in this case, one of the other reason why are we not able to get very good performance is because the volume of data is not so good. Deep learning algorithms usually need high volume of data. We have just 600 images of humans and horses and dogs, which is not that sufficient to be able to get a good model in this place. So yep, that's an idea so far, everyone. That's an idea of how do you train a model, how do you design a neural network using Keras, and how do you sort of program it, right? So that's an idea of working with CNNs and programming CNNs using Python. So done we are with this. Now we are open to questions, right? So we're going to be now taking a lot of questions and getting answers to them. Right. So now we are open to questions, everyone. And yeah, please put your questions. This is where we have seen the implementation in a quick go. It has been a little quick just to cover up in the given time frame. But yeah, so now we are open to questions. Feel free to put your questions. There's a question. I have trained image segmentation, nets unit and segnet on medical images. Got a training dice score about 0.9 and 0.95 respectively. But while testing on data set, training data set score, you got this testing data set on 0.2. Is this a case of overfitting? Yeah, that's heavy overfitting. The model is heavily overfitting. You need to try out regularization or dropout optimization to improve the performance. Or you need to increase the volume of data to make the model get more generalized. CNNs are not used for recommendation engines. For recommendation, the more popular approach are autoencoders and Boolean machines. CNNs can be used with small size data set, but not from scratch. There is a very popular and interesting concept in computer vision called transfer learning. So even with small data set, you can achieve great performance with the help of transfer learning. Right, so that can help us out achieve good performance even with small data sets using CNNs. Demonstrate there is a question, if possible, kindly demonstrate the multimodalities, feature learning, and fusion learning layer network in video for summarization. Well, I may not have exact resource for demonstrating that, but yeah, the idea of the multimodal feature learning is to make the parallel feature learning and extraction of features from that could be from images or from text or from audio, and mix up 2 to 3 features more, to create new features as well, which are not even part of the data. So fusion of features help in extracting such features. For example, let's say we have the pictures of cat and dog, and we have only maybe specific poses of cat and dog. But by fusing 2 or more features, we can also help extract more animals and maybe different types of other features which are not present or visible clearly in the image. Right. So that's a nutshell idea about it. What is the function of dropout? Dropout is used, dropout is used to reset the values of weights within the training process. Point 2 is probability. So when I use dropout point 2, let's say there are 1 million weights or bias at that moment. So out of 1 million weights or bias, it is going to drop 20% of weights, and drop in the sense just reset them to 0. So ultimately it is dropping that many of neurons out of the or resetting the weights of those neurons out of the training process to 0. So dropout is simply to drop, that means reset the values of weights or and bias, that is the number of parameters in that particular iteration, for that particular layer to 0, right? So let's say that at the moment there might be 100,000 weights and bias. So after that layer, if you have used dropout, it will pick randomly 20% of weights and bias and reset them to 0. That's what dropout optimization does. This will stop the neural network to increase the values of weights or change the values of weights much faster. This will make it slower. The changing of the updation of weights and bias will become slightly slower with the help of dropout. Yes, we can definitely save the model for future use. So you can kind of go ahead here. And at the end, you can say model.save model.h5. So h5 is the format. How do we save it? And once I have saved it, I can go ahead here and download it. So I can say download the model. So this is how we can download and save it. All right. So yeah, there's a question. What is global attention upsampling? So first, what is upsampling in general? So upsampling is increasing the size of image. Global attention upsampling makes it what? It also incorporates the features from the previous layers, which could be low level features and mid level and high level features. It incorporates the features from all the layers, and that's how it does the upsampling, which is what you call as global attention upsampling. Standard upsampling could be if I take, let's say if there are multiple layers, there's a lot of downsampling happening up. I got high level features. I just upsample that, increase it to 2 higher dimension. That's the generic upsampling. Global attention is that I incorporate the feature sets from previous layers as well. And by combining them, I do the upsampling. That's a global attention upsampling in general. To get better results, which parameter we should keep change? Is dropout used for overfitting? Dropout is used to handle overfitting. The important hyperparameters in convolution process are 4, as we discussed: the number of filters, the size of filters, the number of layers, and strides and padding at the end. But these 3 are most important: the number of layers, the number of filters, and the size of filters. So keep on changing and customize that. How can I and yes, dropout regularization are used for handling overfitting. There's a question: how can I train and test XLS file with numerical dataset using CNN? You just have to load it and prepare your dataset X and Y, like the way we prepared our dataset X and Y. So you can load it using pandas, and you can just separate the set of features and the set of labels. Right. So the way we have here X and Y are the 2 arrays. You need to create similar arrays and use CNN for that. If it is one linear data, you can use convolution 1D for that. And that's how you can train it. How to use parallel processing algorithms for training network in multi-modalities ID concern. Right. So first thing, when it comes to parallel processing, you can use GPU computing that can help you to do parallel processing. Second is you can configure the package, the library that you're using. So a lot of libraries allow us to do parallel computing by selecting number of jobs to be done parallelly. Right. For example, if you use scikit-learn as a framework, it allows you to select number of processors to be selected at a time. So let's say if my computer has octa-core, i7 you have. So if you have Intel i7, you have 8 cores of processor. So that means 8 models can be trained at a time, or 8 processings can be done at a time. 8 instructions can be executed at a time. So libraries allows us to configure that to achieve the parallel processing, in which we train multiple models parallelly. That's the initial idea. There's a question: if network get overfit, that can we combine dropout with L1, L2 regularization, or use one technique at a time? No, you can combine multiple techniques at a time to avoid overfitting. Batch normalization, or dropout optimization, regularization based optimization, increasing the volume of data using augmentation are multiple solutions to handle overfitting. If network get overfitting, then can we combine? Yeah, so that's answer. What are the feature extraction method in machine learning? Well, there are multiple methods. It depends on what kind of data are we dealing with. If you're dealing with images and pictures, then there are methods of windows, windowing and window scrolling methods like that. Edge detection, corner detection methods could be there. If you're dealing with text, the methods would differ again. Count vectorization, word to wake up vectorization, and TF-IDF vectorization for feature extraction are there in case of text. So it depends on the kind of data that you're dealing with and what sense of information that you want to extract. Because if it is simple classification problem, maybe shapes and the segments of colors, or possibly the the texture could be important features to extract. So in images, you have a variety of methods to extract those kind of features, which are not fixed. But again, in text, it depends of what complexity of features you want to extract. So you can use count vectorization, TF-IDF, or word to wake vectorization, or even there are a lot of other modifications to this. So yeah, that's the nutshell idea. I hope you're good. Let me know, everyone, if you have any questions so far. So I hope we are good so far. We have got the answers to the question, right? So let me know any more questions so far we have. Okay.
Thank you, sir.
Thank you very much. Thank you.
On behalf of Rajkumar Goel Institute of Technology, the entire supporting team, our participants, and on my own behalf, like to extend my sincerest gratitude to Mr. Anshu Pandey for gracing today's session. Thank you, sir, for your interesting words on convolutional neural networks and programming CNN with Python. Please accept our appreciation for such a commendable job. Sir, you have covered all essential elements of neural networks, and your description of how to execute it is remarkable. Our heartfelt thanks to great audiences as well for active participation. Thank you.
Thank you very much.
Thank you all for the active participation. Tomorrow's session will start at 11 a.m. The first session will be by Dr. Sandeep Singh Sanger from SRM, Andhra Pradesh, and the second session by Mr. Chandan Verma from USA. So today's session is very great. I personally thanks Mr. Anshu Pandey for today's session, and let's meet tomorrow at 11 a.m. Thank you. Thank you very much.